An array stores data in blocks of sequential memory. We'll denote an array visually by a large rectangle with many smaller rectangles inside. On the leftmost side, we'll have index 0, which is the first element of the array, and every element that follows will have an index that increases by 1. This entire array is placed in one sequential block of memory, so that as soon as one element ends, the next element begins. Let's look at a couple examples. An example of an array that has the first 10 prime numbers is this first array right here. You'll see in index 0, we have the very first prime number 2. And immediately following this in memory, we have the next prime number 3, followed by 5, then 7. Arrays aren't limited to just having integers. Here's an array that contains 8 characters. Let's see a C++ program that contains a basic array. In C++, here's the syntax to create an array of a fixed size of values. We see the type of this array is integer, and it's going to contain 10 integers. Here are the first 10 prime numbers. We can access each element of the array using square braces. So here values at 3 is going to access the third index in the array. Remember, indices start counting from 0. So 0, 1, 2, 3. And the third element is the number 7. We expect this program to output 7. Let's see what happens when we run arrays example 1. Moving into the arrays directory and moving into example 1, running make. You can see we've already made it, so I'm going to make clean just to really remake it and run /main. And here we see the output is 7. Awesome. So this is exactly what we expect. We expect the third element, or the third index in our array, to be the value 7. Arrays have a few limitations. The first limitation is all data stored in the array must be of the same type. An integer array can only contain integers. A character array can only contain characters. A cube array can only contain cubes. And because we know 2 facts about arrays, we know that all arrays are the same type, and we will know that all of a certain type is the same size. So we know the size of a type, and we know all of the elements are the same type. Knowing both of these things, we can calculate the given offset from any fixed starting point of the array. For example, if we look at this array, we know this is an array of integers. And if we want to know where index 5 is located at, well, we know it's 1, 2, 3, 4, 5 integers past the start of the array. If we look at another array, consider a cube array, we can use a sizeof operator in C++ to ask the compiler to tell us how big a cube is. So size of cube is going to return what the size in memory it takes to store a cube in terms of number of bytes. So if we find out that each cube is 8 bytes long, then we can actually calculate what the offset is to index 3. Index 3 being right here, we know that it takes us 3 cubes to reach index 3. So 3 times 8 bytes means we have to advance 24 bytes from the beginning of the array to access the third index. This is really powerful because we can use a simple equation to access the exact memory location we need to go to. Instead of having to jump to the millionth element by looking at each element in between, if we know we want to look at the millionth index, we do 1,000,000 times the size of the data. This is a really fast operation, and we're going to contrast this against other data types as we explore those. Let's build a C++ program that actually shows off this sizeof operator as well as showing off the memory address. Here's example 2. We see we have the same array of prime numbers, and the first thing I'm going to output is the size of an integer. So we want to know how much memory does it take to store an integer on your computer. Computers are either going to take 4 or 8 bytes to store an integer, and that's going to largely depend on what kind of system you're on and other compiler settings. If it takes 4 bytes, then we're going to see 4 bytes printed out here, and then we're going to go ahead and calculate the offset by looking at the memory address where index 2 is stored minus the memory address where index 0 is stored. We're going to look at how much memory is between index 2 and index 0. So thinking about what we expect is if we expect the size of to be 4, then the difference between index 0 and index 2 is going to be 2 integers, or 4 times 2. So if this number is 4, I expect the output of the offset to be 8. Let's go ahead and run this program and see what happens. I'm going to clear the screen, move into example 2, and run make. then run /main. The first number we see here corresponded to the size of an integer. So the integer on the system is 4 bytes large. The second number is a distance between the index 2 of the array and index 0 of the array. It's 8 bytes, exactly what we expect. So we know they exist sequentially in memory. Let's look at another example. Here in example 3, we have 3 cubes, cube 11, cube 42, and cube 100. We can now print out the size of a cube. When I ran this program earlier, I found out that my cube was 8 bytes large. So storing a cube in memory takes exactly twice as much memory as storing an integer. And I can do the same calculation. How far away is the cube at index 2 from the cube at index 0? Here we have 8 byte blocks of memory. So when we have 2 cubes, they each take 8 bytes. We'll see that we have to travel 16 bytes to access this second element. So what that means is even though we see the exact same syntax, this line of code did not change whatsoever. But because the contents and type of our array is different, it's going to advance by different offsets. So what we expect to see is the first line to be 8 and the second line to be 16 bytes. Different values because we have a cube array instead of an integer array. Let's go to console and see if that works out. Moving into the example 3 directory. Running make. And running /main. Here we see, when we run main, the numbers 8 and 16. This is exactly what we thought we'd see. Awesome. Let's explore another limitation of an array. A second limitation of an array is that an array has to have a fixed capacity. So an array must sequentially store data in memory, and the capacity of the array is the maximum number of elements that can be stored sequentially in that piece of memory. So the size of the array is the current number of elements in the array, while the capacity is the maximum number of elements that can exist. Once we exceed the maximum number of elements in the array, we have to resize the array to allow us to have more memory. Remember, we can't just have an infinite amount of sequential memory because we're going to have other things in memory. So we got to find a block large enough to store all of the elements we care about in the array. And we're going to request a block that's only large enough to store the data we care about right now. As the array grows, we'll resize it. But as part of resizing, we have to allocate a new chunk of memory. When we do allocate a new chunk of memory, we may need to copy the data over. So if the old location has 10 elements here and we want to add an 11th prime number, then we have to copy over all of the original elements. Only then, when we want to write another prime number, 29, can we do that once we have space here at the end of the array. Until we have that space, if we wrote to the end of the array, we're writing in someone else's memory. We saw earlier the standard vector, and the standard vector is something in the standard template library that implements an array as a dynamically growing array. What that means is that internal to the vector, when the vector's capacity reaches the size of the array and it needs to add another element, it has to go about resizing itself. So all of the things you just saw is true about a vector. The vector has a fixed size. The vector has a fixed capacity. Whenever the size reaches the capacity, then we have to expand the vector. Let's look at a very last example that really dives into how a vector works and really see that it is exactly the same thing as an array. So similar to example 3, I have an array of 3 cubes, but instead of having a native C++ array, I have a vector. The initial capacity of the vector is going to be outputted in cubes.capacity. This tells me how many elements can be stored at maximum in my vector. I'm going to add another element, then I'm going to say size after adding. So we expect the size to be 4, because the initial size was 3, and then we're going to look at the new capacity. So it's very likely that the initial capacity of this array will be 3. The new capacity of this array inside the vector is likely going to be larger than 3, and in fact larger than 4, because we really want to make sure we have enough room to add again. So I'm going to expect the capacity after adding to be about double the original capacity, and we'll explore why that is in a future video. So we expect that to grow from 3 to about 6, and we'll see what happens in just a moment. And then we can do the exact same thing we did before and see what is the memory address of cubes at 0 and what is the memory address of cubes at 2. 2 and 0. And we can find out what the memory separation is, or the offset between those two things. Since we know every cube is 8 bytes long, we expect this separation to be 16 if they really are stored sequentially in memory. And then finally, we can actually search through the array to find out where a cube is at. So if we want to find cube 400, we can go ahead and go through the array using a for loop to say, hey, I want to find where my cube is at a particular index. So we're looking for cube of 400, and we're searching for cube of 400 by going through the array one element at a time. Let's run this program and see all of this work together. Going into the example 4 directory, running make, and then running /main. We see the initial capacity of our cube array that had 3 elements is 3. We then add an element, and the size after adding is 4. And as we predicted, the capacity after adding is going to be larger than the size. So it exactly doubled the capacity of the array. We find the memory separation between index 2 and index 0, 2 cubes wide, is 16 bytes. So indeed, the cubes are being stored sequentially in memory. And finally, we found the target at 2, so it showed that we can successfully use a for loop to find a particular index inside of an array. So at this point, you understand the basics of arrays. We are going to contrast this against another form of storage called a linked list or linked memory, and then explore why we might use one or the other. I'll see you then. Linked memory stores data together with a link to the next location in memory, instead of storing all of the data sequentially in memory. By utilizing the link, we can get several advantages over an array. Let's explore how this works, and then we'll talk about the advantages and disadvantages of using this. In C++, we're going to call each list a sequential list of nodes. These list nodes have both the data stored on this left-hand side and a pointer that points to the next piece of the list. So for example, if we look at a list node class, we're going to see that the list node class will be a templated class because we want to store integers and characters and strings and cubes and anything else. So it's going to have a template type T. The class is list node, and in the public section, we'll have both the data. So this is the data piece here on the left. And then we'll have a next pointer that points to the next element in our list. I went ahead and included a simple constructor. This constructor is a list node constructor that takes in data, and it includes data and a next to null. We'll link together 0 or more of these list node elements to form what we call a linked list. And we'll have 2 special properties to this linked list. We'll have a head pointer that we're going to store that's going to denote the beginning of our list. And this is going to point to the very first element. This will point to effectively index 0. And then we'll have a pointer to the null pointer that marks the end of the list. So as long as our pointer doesn't point to null, we know we have not yet reached the end. So looking at the head pointer, if we start at the head, we see the index 0 is 2, index 1 is going to contain 3, index 2 is going to contain 5, and so forth, simply by following the pointers to the next location each time. Looking at the implementation of this in code, we have our list.h file here. Notice that we have a templated class, and this class is class list. In this class, we have a public section that's going to denote a ampersand operator. So this operator ampersand is C++'s syntax to say that we can access a list L. So if we have a list of integers named L, we can say L at 0, and L at 0 is going to call this function. Line 14 is a second member function called insert at front. So we need some way to go ahead and insert elements into the list. In our private area of the class, we have a list node class that's part of the list itself. So notice the list class internally contains list nodes, and this list node contains our data, our next, as well as our constructor. And the very last thing that's part of the list class itself. So notice this list node pointer head is part of the list class. So the list class itself has the add operator, insert at front, a list node class internally to it, as well as the pointer to the head. So all 4 of these things make up a list itself. Let's think about how we might implement that get operation if we want to find out what is at index 4 or index k. I'm going to think about index 4 right now, and then we'll generalize it out to index k. So to access index 4, we need to start at the head and advance to index 0, and then continually advance to index 1, to index 2, to index 3, and then to index 4. Only once we've reached index 4 can we go ahead and return that value. Notice that we have to go through every single node in between. There's no arrow that directs us directly to index 4. This doesn't exist. We have to follow the path of next pointers. So implementing this looks like a simple loop. So implementing this operator square bracket function, retrieving a particular index into a loop, we're going to go ahead and define a through pointer. This is the thing that's going to allow us to advance through the linked list, starting at the head. And while our index is greater than 0, and while we haven't reached the end of the list, we want to continually go through the list. What does it mean to go through the list? Well, the first thing is it means the through pointer should go to the next element. So if we were at this first element, we want to follow the next pointer and set through to be equal to through at next. So this is through's next pointer. So through no longer points to this first node, but through now points to the second list node. And the second thing we want to do is decrement index. So if we start index at 4, after we visited one node, we want to remove 1 from that and make it equal to 3. So as we advance through this loop 4 times, we'll eventually get to through pointing to the actual data that we're interested in. And we don't want to return the list node to the user because the user doesn't even care about list nodes. The user wants to know what's the data at index 4. So we go ahead and return through arrow data. So we are accessing the list node's data element. If we think about the runtime of this algorithm is going to take a lot longer to run than an array. So remember, an array, we could calculate the exact offset to a given element. So if we want to find out what's at element 10,000, we would do 10,000 times the size of the element, for example, 4 for integers, and we know to just advance 40,000 bytes in memory. On a list, we can't do it in one operation. If we want to access the 10,000th element in the list, we have to follow 10,000 next pointers. So as the list grows, the time it takes to access a particular element grows with the size of the list. That's scary, but that may also provide some advantages. We'll do some formal analysis in one of the very next videos. Before we actually run the entire code, we need one other thing. We need to know how to insert into the list. So now I have another linked list. This is just a list of cubes instead of a list of integers. But because this is a templated class, the exact same code for integers works for cubes. So suppose I want to insert a red cube at the beginning of the list. So inserting at the beginning of the list is going to be a particularly easy operation. So here at head, I don't want head to point to the orange cube. Instead, I want to just change head to point to my new red cube. So the very first element in the list is now the red cube. And all I need to do is with the red cube, I need to update its next pointer to be to the orange cube. And suddenly, just like that, I changed where head was located and made sure I reattached the rest of the list. And by doing that, I've created a bigger linked list. And I did that without even looking at any of the elements in the list. So let's see how we might do that with code. It's as simple as we just described. We're going to just do 3 things. We're going to create a new node for a linked list in heap memory. And we want to do this in heap memory because the linked list may live well beyond this function. So we don't want it on the stack because we're going to be using it beyond the scope of this function. So we need to do it in the heap. Doing this in the heap, we see that we're going to create a new list node right here. And the new list node is going to contain our data. And then we're going to say our new list node's next pointer is going to point to whatever the head was pointing to. So our head was pointing to this element right here. And now our new node's next pointer points to the head. And now we want to update the head to point to our new element. And now notice by doing that, our head now points to data, and our data now points to what head used to point to. So we've kept the list intact, we've just added a new element in the front of the list. Unlike an array, the capacity of a list is only bounded by the amount of memory you have on your computer. In contrast, we saw an array had a fixed capacity. We saw that an array had to be resized. Not so with a list. In fact, with a list, we can just keep adding elements again and again and again to the beginning of the list, and it just keeps growing. It's an awesome ability that we don't have with an array. However, similar to an array, a list is going to have every element being of the same type. So an integer list can only contain integers, a string list can only contain strings. This is true with an array and a list. So in both data structures, we're going to be fixed in the way that we store data, in the sense that they have to both contain elements of the exact same type. So let's write a main function that actually sees how this list works. Here on line 9, we create a new list. This is a list of integers, and we're going to insert element with data 3 at the front. So I'm going to have a list that's initially empty, and now on line 12, I'm going to insert up front. So I'm going to insert a new node that has the value of 3, and our next pointer points to null. And then we output what's at list of 0. So list of 0 contains data 3. So we expect list of 0 at this point to be equal to 3. The next thing is we're going to insert 30 at the front. So by inserting 30 at the front, we're now changing the head pointer to point to 30. Its next pointer is going to point to where head originally pointed to, which is 3. So here on line 17, we're going to print out list of 0 at this point. So list of 0 after this insert is going to be the first element on the list, which is 30. And then list of 1 is going to be 3. We expect to insert 3, then print out 3. Expect to insert 30, then print out 30, then print out 3 again. Let's see if this works. Moving into the linked memory directory, I'm going to run make and /main. We see we're inserting element 3 at the front, list of 0 is 3, inserting element 30 at the front, list of 0 is 30, and list of 1 is 3. It's exactly what we expected. So to summarize, linked memory stores data in nodes that are linked together by links or pointers. The basic structure that we have in linked memory is a linked list, which just consists of 0 or more linked nodes linked together. And a linked list provides kind of a more flexible alternative to an array, but with some runtime disadvantages. We're going to formally explore what that means coming up. I'll see you then. Runtime analysis allows us to formalize a method of comparing the speed of an algorithm as the size of the input to the algorithm grows. We're going to contrast two different data structures right now. We're going to contrast an array, a sequential chunk of data in memory, and a list, which is data linked together through list nodes. Remembering back to our array, we can access a given index in an array by knowing the size or the width of each piece of data, and then multiplying the width of each piece of data by the index that we want to access. So it doesn't matter what our index is. Our index may be 1 million, but since we're only doing the multiplication, we can do this multiplication extremely quickly. It takes exactly one multiplication, no matter how much data is in our array. If it's 1 element, 1 million elements, or 10 million elements. In a linked list, if we want to access a given index, so if we want to access index 99, we have to travel through the list 99 times by following next pointers. So as the size of our data grows, the amount of time it takes to access an average element is going to grow as well. Let's look at a table. We want to access a given element, and we want to access element 3. In an array, we can calculate that by simply saying 3 times whatever the size of our data is, and that's going to take one operation. It's going to take one multiplication. In a linked list, we've got to advance 3 different linked nodes. So that's going to take 3 operations to find where our data is at. If we want to access the 4,285th element, well, with an array, we do 4285 times the size. So this, again, is one operation. In a linked list, we have to advance 4,285 next pointers. So we say that's 4,285 operations. If we want to access the 1,250,000th element, again, 1.2 million times the size of is still only one operation. If we're doing this on a linked list, we're going to be following next pointers for a really long time. This is going to be 1,250,000 operations. Now let's think about this in terms of n. If we want to access the nth element, then it still takes n times whatever the size of the data is. So that is still one operation. In a linked list, that is n operations. So we say that no matter how many elements in the array, we're always going to be able to access the nth element in what we're going to call big O of one time. On the other side, in a linked list, we're going to take n operations, so we're going to call this big O of n time. And big O is just a syntax that lets us know that this is how the function grows in time complexity relative to the input. Let's think about a resizing of an array. So if we want to resize an array, one strategy we can do is that every time we need to resize the array, we're going to resize the array enough to put in the next element and store one more element after that so that we don't have to do this work all of the time. So here we have an array of 6. We need to resize it to 8. So I'm going to go and copy over this data, 2, 3, 5, 7, 11, 13. Then I'm going to enter my next prime number, 17. And I've left this open space here so that I don't have to do this process right away again. I've got room for the next piece of data that's coming in. So I ultimately had to make 6 copies of our data to our new array. And then I have room for 2 more pieces of data, one that I use right away. So this strategy is that whenever the array is full, we want to add 2 more to the capacity. So I'm going to formalize what this takes as our capacity grows to n. Initially, our array is going to start out with a capacity of just 2. And this is going to happen in the very first round. And then after the first round, we're going to have to make 2 copies of our data when we resize this array to be 4. And then we're going to have to make 4 copies when we resize this data to be 6. We're going to make 6 copies, 8 copies, 10 copies, and so forth. So you'll see that we denote the number of copies we have to make at each level until the last level when r is equal to n over 2. So we know that this is going to be n pieces of data, and we know it's going to take, we're going to have a round of resizing every other piece of data. So n over 2 pieces of data, which we're going to call r, is going to require 2 to the r minus 1 copies. Let's go ahead and actually add up the total number of copies that it takes over the entirety of the algorithm expanding from an initial array of capacity 2 all the way down to when the array is the capacity of 2 times r. So here we have 2 copies, 4 copies, 6 copies, 8 copies, 10 copies, all the way up to 2 to the r minus 1 copies, where r is equal to n divided by 2, because remember, we're resizing every other time, so n divided by 2 times. And what we want to do is we want to change this into a syntax that we can easily add together, because 2 plus 4 plus 6 plus 8 is kind of rough. Instead, in terms of number of resizes, this is going to be 2 times 1, 2 times 2, 2 times 3, and so forth. So here we have 2 times 1 plus 2 times 2 plus 2 times 3 plus 2 times 4 plus 2 times 5. So the total amount of copies made is going to be the sum of 2 times k when k is equal to 1 all the way up to when k becomes r. From k equals 1 to r, we're going to have 2 times k, so this is the total copies. Working out this math a little bit, 2 times k, as you might remember from a introductory calculus class, is going to be 2 times r to the plus 1 over 2. If we go ahead and cancel out the 2's and distribute the r's, we have r squared plus r. So we know the sum of all of the required copies is going to be r squared plus r copies. So we know two things. We know that the total number of copies is r squared plus r. We did this by a summation. And we know that the relationship between r and n is r is equal to n divided by 2. So we can go ahead and substitute r back in for n because we really want to know how much this grows in terms of the number of data, or n, and we don't really care about how big r is. R doesn't mean anything to our final analysis. So we're going to go ahead and substitute n for r, and we get n over 2 squared plus n over 2, and the final equation we get is n squared plus 2n divided by 4. In big O notation, what we want to do is we want to actually just express the largest term without any of the constants. The largest term in this equation is n squared. So n squared is larger than 2n, it's larger than the constant 4. We'll drop everything that's not the largest term, and big O notation is always going to note the largest term in an equation. So here we have that the total amount of time for all of the copies is going to be n squared total time. So let's see how this differs if we use a different strategy. Our other strategy is let's double the capacity every single time as opposed to just adding 2 each time. So if we double the capacity, starting with an array of size 2 again, the first time we do 2 copies. The second time we do 4 copies. The next time we do 8 copies. And so forth until we do 16 copies, and eventually we do 2 to the r copies, where r is going to be the logarithm of the total number of elements. So again, doing the summation of all of these things, we have a sum from k equals 1 to r of 2 to the kth power, because this is 2 to the k, 2 to the k, 2 to the cubed, 2 fourth, 2 to the r. And we know that this is equal to 2 times 2 to the r minus 1. Just like before, we have 2 equations. We have the number of total copies, which is 2 times 2 to the r minus 1, and the relationship between r and n. And now r is equal to a logarithm of n. Doing the same substitutions, we see that if we substitute log n for r, we get 2 to the log n power minus 1 times 2. Because 2 to the log n of n is just equal to n itself, we're going to substitute this value for n. So we have the equation 2 times n minus 1. Here, looking at the dominant factor, we have essentially 2n minus 2. Dominant factor is 2n. Dropping the constant, the only thing that grows is n. So we say the total runtime of all of the operations needed, if we're doubling the size of the array, is big O of n. This is much less than n squared. So what we see is if we analyze the runtime, we can see that the strategy actually makes a big difference. Instead of taking n squared time to do all of the copies, we take just n time. This is awesome. So here's an example of where the strategy we use to resize an array makes a difference. So strategy number 1, growing by plus 2 each time, is going to take n squared work. Strategy number 2, doubling each time, takes O of n total work. Now notice we talked about total work at each point. What we really want to care about is how much work is done every time I insert. If the total work to insert n elements is O of n, and I'm doing n different inserts to do all of that work, then the total work O of n divided by the number of inserts I do is going to be equal to O of 1. And we call this amortized running time. Because if we look at this diagram, we see that most of the time, looking here between rounds 3 and 4, we see that we just insert, we copied over 8 elements, then we get a free insert, 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 we get a free insert. Most of these operations don't require any copying at all. Only once every so often do we have to actually then copy over all of the data and move forward. But then we can insert all of that data again before we have to do another copy operation. So the average time on an average operation is going to be O of 1 time. That on average, resizing the array takes a constant amount of time, amortized across the entire runtime. So let's look at how this all comes together. We looked originally at the fact that we have a table that we filled out at the very beginning of this video, where the access time for an array is always O of 1, and the access time for a linked list is always O of n. What you've just been introduced to is runtime analysis. And runtime analysis allows us to formalize a method of computing the speed of an algorithm as the size of the input grew. You saw two different runtime analysis. You saw the runtime analysis of what it takes to access an element, and you saw the runtime analysis of resizing an array. We summarize runtime analysis in what we call big O notation, that we leave out everything but the most dominating term in the equation. So the most dominating term may either be O of 1, which we call constant time. That means it's going to run approximately in the same amount of time, no matter how big the data is. For example, looking at our array and getting a particular index out of our array runs an O of 1 time. It might run in linear time. As the data grows, the running time is going to grow at the same rate. It's linear, or O of n. And then we have O of n squared, or polynomial time. This is the total amount of work, for example, if we resize the array by adding 2 elements at each step. This O of n squared, or polynomial time, is going to be much slower than linear time, and that's going to be much slower than constant time. So as we do analysis, we're going to want to try and achieve O of 1 time if at all possible. Otherwise, we may see O of n or n squared time. We'll keep looking at some more analysis in the next video, so I'll see you there. Arrays and linked lists are both ordered collections of data. There's several key operations that we want to compare and contrast between these two collections. We've already talked about accessing a given index in the collection. We saw in a previous video that an array we can access in O of 1 time, that we get direct access via a formula, where we must traverse every single node in a list in order to get to the particular index. So an array takes O of 1 time to access a given index, a list takes O of n time. When we insert at the front of the array, we know that we need to resize the array every so often. By inserting at the front of the array, we can double it every single time and give us an amortized access time of O of 1. In a linked list, we saw that inserting at the beginning of a linked list is simply O of 1 time. It was in fact just 3 lines of code. By adding the new data at the beginning, setting the new data's next pointer equal to the old location of the head, and setting the head equal to the new node we just inserted into the list. Let's think about finding data. Given data, how do we go about finding data inside of a collection? So if I want to find the orange cube in an array, I have no other choice but to start at the beginning and look at the first element, then look at the next element, then look at the next element. Aha, I found the cube. So the amount of time of looking at every single element is going to take operations equal to the amount of the data in there. So to find the orange cube, we need to check every single piece of data. So that's going to take O of n operations to find our orange cube. Suppose we want to find the purple cube in our list. If we want to find the purple cube in our list, we need to look at the head of the list, start looking. Nope, not the purple cube. Go to the next one. Not the purple cube. Go to the next one. Not the purple cube. Go to the next one. Not the purple cube. Go to the next one. Not the purple cube. And so forth. So eventually, we're going to find the purple cube, or possibly not find it, but we're going to also have to travel through every single element in the list to potentially find it. So we also say finding an element in a list is O of n. So to formalize this, given data, find the location of that data in the collection. Well, in an array, it takes O of n to find a particular piece of data. In a linked list, it also takes O of n time. So it takes the exact same amount of time in both of these structures to find a piece of data. But could we do better? So looking at the code to find an element inside of an array, we saw this code in our arrays lecture. And in example 4, you'll see that lines 29 through 34 has the code to find an element. In the list.hap class, we saw that we have a find function that finds the data inside of our list. So you have the code for both of these if you go back to linked memory or the arrays, and you can actually play around with this find algorithm. But I'm going to argue that we can improve this find algorithm if our data is sorted. So it's the same objective. We want to, given data, we want to find out the location of that data within the collection. But the only difference here is now we know that our collection is sorted. So if we want to find 17, we could go and say 2, 3, 5, 7, 11, 13. Oh, I found 17. I could use my O of n strategy called a linear search. But I think we can do better. I think if I want to find 17, it's sort of like a phone book. If I want to find something in a phone book, I don't start at the beginning of the phone book. Instead, I start in the middle of the phone book. So here, if I want to find 17, I'm going to jump to the middle of the array. And by jumping to the middle array, I can see, is 13 greater than or less than 17? Well, 13 is less than 17, so I know that 17 must appear on the right-hand side. So I can eliminate half of this data from my search completely. I can then repeat this process with the rest of this data and say, is 19, the middle of the what's left, greater than or less than my data? Well, it is greater than, so I know my data must be on the right-hand side. And now in just 3 operations, I found the number 17. I found my data in the array. And I did this by looking at half of the data each time and eliminating half of it. The array has to be sorted, but we use a strategy called a binary search. By using a binary search, we were able to eliminate the need to look at every single data, and we were able to cut in half each time. When we cut something in half, that's a log base 2 operation, which we denote as log n. So when we write LG, that denotes simply log base 2 of n. So this is a log n operation. So we say the total running time is O of log n because we're constantly cutting our data in half and half and half and half. So that's awesome. So we know we can do better than O of n time if we have a sorted array. Let's look at a list. Inside a list, here we have a list that is sorted, just like our array, and we want to find 17. So how do I jump to the middle of the list? I can't. There's no magic pointer that points to the center of the list. And even if we had a pointer that pointed to the center of the list, as we added to the beginning of the list, that pointer would be out of date very quickly. So there is no way to jump to the center of a list. Instead, the best we can do is still travel the list. Look at the first element, look at the second element, look at the third element, look at the fourth element, look at the fifth element, and keep going until we find 17. So only by doing a linear search through the list can we find an element when we have a linked list. So a linked list, even if the data is sorted, is still O of n time. So given data, find the location of data, our entire analysis is going to be an unsorted array takes us O of n time, a sorted array takes us log n time, and a list takes us O of n time. You should not only know these runtimes, but you should also know the intuition behind these runtimes, so that when you see a similar data structure, you'll be able to drive these runtimes and go through the analysis of understanding why they work the way they work. So I'm going to look at one last operation that is often going to prove extremely useful. So given an element, we want to insert a new element immediately afterwards. So this is essentially insert after operation. So if we have a linked list node, we want to know how much time it takes to insert after that linked list node. Given an array index like index 4 inside of an array, I want to know how much time it takes to insert right after a given index. So if we have a linked list node, or if we have an array, how much time does it take to insert after that element? So looking at an array, if we want to insert a purple cube after the orange cube, then if we look here, we need to stick a purple cube right in here. So with an array, all of this data is sequentially in memory. What that means is there's no way we can just slam that purple cube right in the middle there. Instead, what we have to do is we have to copy the data that's already after our orange node, move all of this data over, and only once we moved all of this data over do we have room to insert the node. Since we have to keep moving all the data, either all the data to the left or to the right, we can move in either direction. But if we insert an element at the very center of the list, we're going to have to move n divided by 2 data moves. So by moving n divided by 2 elements, Using big O notation, we know that this is big O of n total moves. So the amount of time it takes to insert after a given element is O of n. On the other side, if we look at a list, so given an element, so given a linked list node, given this linked list node right here, how much time does it take to insert after our linked list node? Well, we can just create a new list node, put this purple cube in there, and change this next pointer to be here, and put this next pointer to our gray cube, and done. So insert after our known linked list node, this is O of 1 time. It doesn't matter if this data is 1,000,000 nodes wide. We never have to copy over any data. We just have to stick one thing right in there, repair a few pointers. It's 3 lines of code and no loops whatsoever. This is O of 1 time. So if our objective is to insert an element, either a linked list node or an index, immediately after a given element, then it's going to take O of n time in an array or O of 1 time in a list. Likewise, we can see that the delete after operation is going to be the exact same as insert after. If you think about removing the next element in an array, we have to copy over all of our data and move it back to make sure our array still is sequentially in memory. While a list, we can just repair the pointers. So whether or not we have insert after or whether or not we have delete after, if we have a given node with an array, it takes us O of n time to delete or insert a node right afterwards. In a list, it takes us just O of 1 time. So you've seen that arrays and lists are both ordered collections that can have trade-offs between the runtime and the flexibility of their implementation. We're going to build data structure on top of arrays and lists, and we're often going to question, what do we want in the base of our data structure? Do we want an array or do we want a list? And these two fundamental linear data structures are going to build everything else that we're going to build in this class. I'm looking forward to building these with you, and I'll see you there. A queue is a first in, first out data structure, similar to waiting in line. We'll represent a queue visually by having an array or a list or any type of container inside of a series of lines. We'll see an inner point and an exit point. So you can imagine if you're waiting in line for a cup of coffee, the first person to arrive in the line will get their drink first. People arrive at the back of the line and move through the line in the order which they arrived. This kind of model we'll model with a queue. When we talk about data structures, we'll always talk about a data structure in terms of their abstract data type, or how data interacts with the data structure without talking about an implementation. So an ADT is not an implementation, but it's a description of what the data structure does. Then we'll explore the implementation after knowing the description. The abstract data type for a queue is going to have 4 different functions. The first is we need to be able to create a queue, and that will create an empty queue with nothing in it. We need to push data into the queue, and that will add data to the back of the queue. When we want to remove data from the queue, we'll pop the queue, and popping the queue will take the first element of the data and bring it out. And finally, we need some ability to determine whether or not the queue is empty or not. And the empty functionality will determine if the queue has anything in it or is completely empty. So let's consider simple operations on a queue, thinking only about the abstract data type and what we know about how a queue functions. We first are going to create a queue of integers. So we'll go ahead and initialize this queue, and we know it's going to contain integers. And we'll go ahead and push the number 4 onto the queue. So we'll add 4. 4 is ready to be the first person off the queue. The second thing we'll do is we'll push number 2 to the queue. And then finally we'll pop a number from the queue. Because the queue is going to take the first thing to arrive, 4 is going to get popped off the queue, removed from the queue, and now 2 is the next element to be removed. In C++, we actually have a queue provided for us by the standard library. This is an std queue. Similar to a standard vector, we can use a standard queue by doing stdq. It's a template type, so here we have a queue of strings. Here I'm going to in-queue 3 different elements by saying push orange, push blue, and push Illinois. We expect orange to be first. Behind orange is blue. And behind blue is Illinois. On line 21, we see out the first pop, so we get the Q at the first element. So we expect this to print out orange. Since orange has been popped off the top of the Q, we now go to the next line, line 25. We add Illinois to the Q. We see the inner here is at the end of the Q, so we'll add Illinois. Sorry, we'll add Illini, not Illinois. And then we do ST second pop is queued up front. So what's at the front of the queue now? It is blue. So the output of this program, understanding our queue, is that after adding 3 elements, when we pop off an element, the element should be orange. After adding Illini, we pop off another element, and it should be blue. Let's see if this logic matches it when we run the implementation. Moving into the queue directory, running make and /main. The first pop is orange, exactly what we expect. The second pop was blue, exactly what we expect. So our logic in the code matches up. But let's actually understand what the queue does internally and how fast it runs. Internally, a queue can be implemented with either of our 2 basic data types that we've already discussed. We can have an array-based queue or a linked list-based queue. In an array-based queue, an array is going to sit in the queue and will have an index for each element in the array. The array will be an initial size, and again, we can expand it by doubling the size or shrinking it by halving the size as we need to. When an element arrives in the queue, we'll simply add it to the queue. And we can continually add items to the queue as they arrive. We only need to ensure that the elements as they arrive is placed further back in the queue than all of the elements that currently exist. In this array-based queue, notice that we can always have a counter to determine the index where we should enter things next, and we can always keep track of the index. For example, here we might be at index 8 of where we should be removing from the queue. There's a number of different ways to set up the arrays, but so long as you keep track of where the insertion point is and where the removal point is, or where the pop and push points are, we can always just adjust them by adding one or subtracting one and resizing the array as needed. All of these operations are just operation of indices and are always going to run in O of 1 time. A list implementation is slightly different. We're going to have a linked list, and we know in a linked list we can insert at front in O of 1 time. By inserting at front in O of 1 time, we can continually add things to the head as they arrive into our list. What we absolutely don't want to do is to have to traverse through the entire list. Instead, what we want to do is we want to store a new pointer called a tail pointer that's maintained at the very end of the list. This tail pointer will allow us to always access the last element of the list and is something we can easily maintain. The last thing that we need to do to maintain this tail pointer is in linked memory, instead of just linking our memory forward, let's make sure we link all of our memory backwards as well. So if we do this, whenever a new element arrives, we can always add it directly to the head. We know that adding to the head takes O of 1 time. On the other side, when we have a tail pointer, we can always find the element at the very end in O of 1 time. We can remove this element and update the tail pointer to the previous element if we have this doubly linked list where we have back pointers. So our update also takes O of 1 time if we're careful with the design. So using the base idea of a list, we can implement a list by adding a few minor features and get an O of 1 time for both push and pop onto a list, just like we were able to with an array. So summarizing all of this, creating a queue data structure is going to take O of 1 time to create an empty array and O of 1 time to create an empty linked list. We argued that push and pop were both O of 1 time, so long as we have a doubly linked list for a linked list, and so long as we do an intelligent resize, where we're doubling the size every time we run out of room in our array. Notice that we have O of 1 operations in the array because we're always inserting it at the front of the array and removing from the back of the array. And finally, we can determine what the size of each of these components are in O of 1 time. So when we're building a queue, every operation we perform on a queue is an O of 1 time operation. That means it doesn't matter if we have a million things in the queue or just one thing in the queue. By using a queue, we guarantee there's going to be a constant runtime, no matter how large the queue grows. So a queue is a first in, first out data structure that mimics waiting in a line. A queue may be implemented with either an array or a linked list, and by using wise implementation for both of these structures, we can build a queue that runs in constant O of 1 time. This is going to be a powerful data structure that we're going to use to manage a lot of things as we go forward in this class. The sister data structure to the queue is the stack, and I'll talk about that one in the next video. I'll see you there. A stack is a last in, first out data structure that is similar to a pile of papers or a stack of papers on a desk. So if you imagine a paper that has the number 4 placed on your desk, and then on top of the paper with number 4, you put a paper that has the number 5. And on top of number 5, you put the number 8. And on top of number 8, you put the number 3. As you look at the stack, the paper on top with the number 3 will be the first paper you grab. And in that way, the last paper you put down is the first paper to come out. We're visually representing the idea of a stack by having the same syntax as the queue of a list that has barriers on both sides, and then having the input and output arrows right here at the same spot. Similar to all data structures, we're going to look at the abstract data type first. There's 4 operations on a stack. A stack can create, which creates an empty stack. It can push, which adds data to the top of the stack, can pop, which removes data from the top of the stack, or it's empty, which returns whether or not the stack is empty or not. Notice that this ADT is identical to the queue ADT. We can consider an example with a stack. Let's consider a stack of integers. We're going to place 4 on top of the stack, and then we'll place 2 on top of the stack. Next thing is we'll pop number off the top of the stack. Looking what's on top of the stack, we remove 2. So 2 comes out of the stack when we're using a stack data type. The C++ standard template library provides us a stack as part of the base library. ststack initializes a stack. Here is an ststack using of standard strings. The variable name is s. We're going to go ahead and push 3 things on this stack. So I'm going to go ahead and draw out my stack. I'm going to push orange onto the stack, then push blue, and finally push Illinois. I'm now going to go ahead and pop off the element by looking at the top element and then popping off. So I'm going to take Illinois, and I'm going to go ahead and output this out. So Illinois is the first thing that's popped off the stack. Since I popped it off, I can remove it altogether. Next thing, I'm going to add Illini. Goes in, goes to the front of the stack. And then the second pop, I can go ahead and look at that top element. It is Illini. So this code is identical to the code we saw for a queue, except for the fact that we use a stack here instead of a queue. The push and pop operations are the same, but the way they enter and exit from the data structure changed dramatically. Here we expect the result to be Illinois and Illini. Let's see what actually happens when we run this code. Here at the console, I'm going to move into the stack directory, run make, and /main. Our first pop indeed got Illinois, and our second pop got Illini. So we see we have code that we can play around with and see how a stack works. Let's examine how we might build a stack if we wanted to build one ourselves. A stack can be built with any type of collection, and here we're going to examine a stack with an array-based collection. Here with an array, as we insert elements in the stack, we likely will put the element at the very end of our capacity. So we'll put it at the last available index. So as I insert 4, 2, 8, 7, then I will store a counter on exactly which index I'm at. So here I've been inserting things at index 5, and the next index will be inserted at index 4. When I need to remove, I'll remove from index 5. If I run out of space and I've reached index 0, I can simply expand the array out this way and give myself more space to insert more elements. Let's look at an example. I'm going to label the indices of our array. And after labeling the indices of the array, I'm going to keep track of the insert location. So I'm going to be inserting at index 4. So I'm going to go ahead and push 1 onto the stack. I'll update my insert location to 3. Push 2 onto the stack, update my insert location to index 2. Push 3 onto the stack, and then pop out the element at the front of the stack, popping out 3, removing it from the array. I'm going to go ahead and push 4, which now gets inserted here. Push 5. Pop out the top element of the stack. We're going to pop out 5. Remove it from the stack. Here we're going to need to push 6. Push 7. And we're about to push 8, but we're out of space. So since we're out of space, we know we're out of space because the next insert location is going to be effectively -1. We don't have an index at -1. So instead, we're going to need to expand this array. What we'll simply do is double the size. So we'll create an array with 10 indices and copy over the data. 1, 2, 4, 6, 7. The next location to insert it is going to be here at the new index 4. And we can go ahead and insert 8. Awesome. A linked list is even easier. Thinking about a linked list, when the stack is initially empty, we're going to have a linked list that simply points to null. When we add our first element, we simply update the front of the list and add that element. When we add a second element, we just insert the front of the list again. And now we have a list with 2 elements. So here is a stack that has 4 elements on it already. Maybe 4, 2, 8, 3. When we want to remove the front element from a list, we just remove this front element and update the head pointer. It's only 3 lines of code. Extremely simple. So the implementation of a stack in a list is quite easy and only requires operations that only take a few lines of code. These are all also O of 1 operations. What we see here is as long as we're intelligent about the data structure we use and use optimal implementations, such as doubling the size of the array when we're pushing and popping from the array, we can see that all of our operations on a stack is O of 1. Unlike a queue, on a stack, a singly linked list is sufficient for a stack because we don't have to store a tail pointer. All of our operations happen at the front of the list. A stack is a last in, first out data structure that mimics a stack of papers on your desk. A stack might be implemented with an array or a linked list, and all of the operations on a stack runs in O of 1 time. What this means is no matter if we need a stack or a queue for our purpose, if we use either of those data structures, we can ensure that all of those operations are going to take a fixed constant amount of time, no matter if there's 1 element of data or 1 million elements of data. This is a powerful fact that will allow us to build better and stronger data structures. We'll keep diving into data structures more, so I'll see you then. Up until now, we have discussed purely linear or flat data structures. Today, we're going to discuss a new series of data structures that provides us the ability to have complicated data and relationships such as a parent, child, and sibling relationships. This data structure is called a tree. Let's dive into what this means. This is one of my favorite trees in the world, and this tree maps all of the Mario games that were created in the entire Nintendo franchise until 10 years ago. As part of this tree, you can see that there's an original game that included Mario. That was Donkey Kong. And from there, there's a ton of different games that run the entire lineage of Mario games, going only to Mario Galaxy. And there's been probably hundreds of games since then. So seeing this Mario family line, we see it starts with a single node. And really, these are kind of precursors to the actual first Mario game. And the first true Mario game is really here. And we can really consider this the root of the tree. From there, we can see that the root of the tree has several branches. My personal favorite is Super Mario Bros. RPG. Great classic if you've ever played it. But let's actually talk about trees, not in terms of a specific tree, but terminology that can apply to every tree possible. And in fact, this video is just going to talk about the terminology so that after this point, we can be very clear when we're describing this data structure. Every single element in our tree, we're going to call a node. And we're going to always denote a node with a circle. So you'll say, see, here's a tree. And in this tree, we have a number of nodes. Nodes are always connected to another node by an edge. In a tree, an edge will always be directed and will always be directing the edge away from a root. In computer science, we often say that we grow trees backwards because it will represent a tree with the root on the top compared to a normal tree, then will grow out by going down instead of going up. But you can really think of an original tree, just turn it upside down. So a tree must always contain a single root node, and the root node must have no incoming edges. So the topmost node of the tree, as we draw it, has nothing coming into it. All it has is nodes going out of it, and every tree must contain a single root. So there's only one node that has no incoming edges, and that node must be the root. Nodes that have no outgoing edges are called leaf nodes. These are at the base of our tree, and these, just like a normal tree, we're just going to call them leaves. And these leaf nodes can be found at any level, but the only requirement is they have no outgoing edges. In our trees, our node will store our data. So here in this tree, we've stored the first 10 or so letters of the alphabet. In this tree, the nodes contain the data. Edges, on the other hand, are often never labeled, and they contain no data. In fact, we'll identify the edges just in the names of the nodes that they connect. For example, this edge from K to M, we'll just call this KM, because this is the edge that starts from K and goes to M, and it connects the node K and the node M. So we will very rarely ever name an edge, and our edges will never contain data. All of the data that we're going to store in this data structure will always be in the nodes. Every node except for the root node will have something we refer to the parent node. This works just like a family tree. One level up from you in the tree is going to be your parent. For example, the parent of B is A, since B has an incoming edge from A. The parent of K is D. Looking at the incoming edge again, parent of L is also D. On the flip side, a node's children are the node that have that node as a parent. So it's possible for a node to have anywhere from 0 children to an infinite number of children. Well, every node but the root has just a single parent. So notice that node A right here, node A has 3 children. Node C, a leaf node, has no children. So leaf nodes have no children because they have no outbound edges. And M right here has just a single child. So we see a node that has 3 children, a node that has 3 children, a node that has 1 child, and a node that has 6 children. So these type of relationships on the tree work just like an ancestral tree. And all of the ancestry terms that you're used to really do apply to the trees. Siblings, a sibling of a node is something that's on the same level and shares a parent. So B and D are siblings. An ancestor works just like a normal family tree. A grandchild or a grandparent works just like a family tree. You can have multiple grandchildren, just like you could have in a family. But because our nodes don't actually marry, you only have a single grandparent. Finally, we want to define exactly what it means to be a tree. And a tree, 3 conditions have to be true. The tree must have a root, the tree must have directed edges, and the tree must not contain a cycle. So what this means is if I were to have a edge from M to D, suddenly we can travel from D to K to M back to D in this big loop. If we ever have a loop, we're no longer a tree. So long as all of our edges travel down a level deeper, so notice all of our edges are down, then we can never have a loop. Because to have a loop, we have to move an edge up. So as long as all of our nodes face down, we can easily check any sort of diagram and say, okay, yep, all of the nodes' edges face down, therefore we must have a tree. We say this tree is a rooted, directed, acyclic structure. And we'll explain what this means more as we talk about general trees or graphs later in this class. So the big things to take away is trees are formed with nodes and edges. Trees must be directed, rooted, and acyclic. And the relationship between nodes and trees follows a classical ancestry pattern. It's got parents, it's got children, it's got grandchildren, it's got a grandparent. It has ancestors, and it has descendants. All of the terms that you're accustomed to from your own family, we're going to use here in computer science. So now that you have your tree terminology, let's dive in and look at particular types of trees that are particularly useful as a data structure. I'll see you there. A binary tree is a tree where every node has at most 2 children. If we look at some sample trees, here's tree 1, which has a root right here, and the root has 2 children. The right child has 2 children. This has 1 child. This has 1 child. Everything looks good. Here at tree 2, we have a root. It has 2 children. The left child has 2 children, and the right child has 2 children. This is also a tree, and is specifically a binary tree. And finally, this last tree, we see here's the root. Tree 3 has 1, 2, 3 children at the root. Because we found a node that has more than 2 children, this is not a binary tree. So when we talk about binary trees, we're going to be specific, as I was earlier, about a left child and a right child for every single node. So here's a left child, here's a root node, and here's the root node's left child, here's the root node's right child. So T sub L, T sub R for a given node T. So we can look at the implementation of how we might implement this in code. This binary tree structure looks nearly identical to our list structure. So remember in our list, we had a list and then a list node. Here we have a binary tree and a tree node. In our list data structure, we had T ampersand data, it's a data by reference. Here in our tree node, we also have data by reference. In our list, we had a list node star, and then we had a next pointer. Here we have a left and a right pointer. So instead of a linked list, where a linked list has just a single pointer to our next piece of data, a tree node has a pointer to our left children and a pointer to our right children. So it's essentially a linked list with 2 pointers at every node instead of just 1. This structure is exactly what you saw in a linked list. This shouldn't be a surprise. So one property of a binary tree that we're going to talk about is the height of a binary tree. And this really does apply to all trees, but we're going to pay specific attention to the height of binary trees. The height of the binary tree is the number of edges that exists in the longest path from the root to a leaf. So looking at this tree right here, the longest path is going to contain 1, 2 edges. So because this path contains 2 edges, we say the height of this tree, or h, is equal to 2. Here in the second tree, here is our root node. If we take the left child, we see that its height's only 1. We only travel 1 edge. But we need to find the longest path. So traveling down the longest path, we see 1 edge here, 2nd edge here, 3rd edge here, 4th edge here. So the height of this tree is 4. So the height of a tree is defined in terms of the number of edges that we travel from the root down to the leaf. One property that exists of a binary tree is we can have binary trees which are full. And a binary tree is full if and only if the nodes have either 0 children or 2 children. So if we look at a binary tree and look at every single node, we need to check this has 2 children. Okay. This node has 2 children. All right. This node has 2 children. All right. This node has 0 children. That's fine. 0 children, fine. 0 children, that's fine. 0 children, that's fine. However, if we look at this other tree that we've been exploring, the root node has 2 children. That's fine. This left child has 0. That's fine. This right child also has 2. That's fine. This node, though, it has only 1 child. Because it has only 1 child, we can say that this tree is not a full tree. While the tree here is full. In addition to being full, we might want to talk about a perfect tree. A binary tree is considered perfect if and only if all of the interior nodes have 2 children and all of the leaves are at the same level. So looking at our 2 sample trees, we see that all the interior nodes have 2 children. And here at this last level, all of these leaves are the same level. On the other side here, we have interior node has 2 children. This is a leaf node. It's got 0 children. Interior node, 2 children. Awesome. Ooh. Here we have a node that's interior to the tree. It's not a leaf node, but it doesn't have 2 children. Because of that, it's not perfect. Notice that we can also look at a slightly different version of this first tree that we examined. Suppose I removed this rightmost leaf. Is this tree still perfect? This tree is no longer perfect because notice an interior node has just 1 child. The last property I want to talk about is a tree being complete. So we consider a binary tree to be complete if and only if the tree is perfect up until the last level and all of the leaves on the last level are pushed to the left. What this means is we have a perfect tree here. So this is a P of height 2. So it's a perfect tree that has height 2. Notice that all of the nodes have 2 children and all the leaves are at the same level. So this looks good. Here, we have a perfect tree up here. So we have a P2 right here. But then underneath the P2, we do have a few extra nodes. So on our very last level, we have to ask, are all of these nodes pushed to the left? And in fact, they are. So we have a complete tree if and only if the tree is perfect up until the last level. And then on the last level, the few dangling nodes we have are all pushed all the way to the left. And we're going to see this idea of a complete tree is extremely important once we start talking about heaps. So with these definitions, we can have some fun puzzles to ask. So one puzzle is a full tree complete? And to answer this, we don't just need yes or no, but we actually need to understand and justify either why it's a yes or provide a counterexample if it's a no. So is a full tree complete? Well, a full tree just needs to have all of the nodes having 0 or 2 children. So here's a full tree. So it's full because it has 2 children, 0 children, 2 children, 0 children, 0 children. Is it complete? Well, a complete tree has to be perfect up until the last level. So this is a perfect P1. But then all of the nodes on the last level have to be pushed to the left. Have these been pushed to the left? They have not been. So this tree is full, but not complete. So here's an example of a tree that is full, but not complete. So is a full tree complete? No. Is a complete tree full? Well, this one, we can look at this example right here. We argue that this was a complete tree. This tree was a perfect tree of height 2 with a few nodes at the very end. A complete tree requires us to have every node having 2 children. Here's a node that just has 1 child. Because this node has only 1 child, this complete tree is not full. So is a complete tree full? Not necessarily. We spent this lecture talking only about the definitions and particular formalities about trees, so we can discuss in detail how these trees work and begin to build complicated data structures with provable runtimes by understanding the properties of trees we create. So in the next lectures, we're going to start to dive in more about binary trees. We're going to talk about adding data to binary trees and start to organize data around the idea of a tree to create an awesome data structure that's going to run faster than an array or a list in certain circumstances. I look forward to going through those, and I'll see you there. One of the most important aspects of trees is how do we get the data out of a tree? How do we visit every single node? And in what order do we visit these nodes? All of these topics is covered under this idea of a tree traversal. And there's several different ways to look at a tree and several different ways to do a tree traversal. Let's take a look at a sample tree. Here's a tree that contains a total of 9 nodes. These 9 nodes are rooted at the plus node here at the root. And then on the left-hand side, we have minus. The right-hand side, we have times. We can see that if we view this tree in one way, we could possibly get a tree that has a math equation. Let's see how we might do this, and let's look at different types of traversals. The very first form of a traversal is going to involve looking at every single node and then deciding to go left, right, or to shout that node out as we visit it. Let's see what happens if we go shouting out the node first, then go to left, and then go to the right. So looking at this tree again, if we do shout first at every node, then travel left, and then travel right, here at the plus node, we're going to shout it out. So the first thing we're going to say is plus. Awesome. Then, since we've shouted it out, we're going to go left. So here we're going to shout it out again. We shout out minus. Then we're going to need to go left and right. So let's go left. Here at this node, A, we're going to shout it out, and we shout out A. Finally, we need to go left. Left goes nowhere. Then we come back to A. We need to go right. Right also goes nowhere. So we're completely done with A, and now we can move back up to minus. We finished the left subtree. Now we can go to the right subtree. Here in the right subtree, we're going to shout out division. Then we're going to go left. Going left, we get to B. We're going to shout out B. And then go to B's left, which is nowhere. B's right, which is nowhere. And now finally done with B, we can return to the division. We've done shout, we've done left. We now need to go right. Shouting out C. Left and right goes nowhere. Done with C, done with division, done with minus, back up to the plus, the root node. Now we need to go to the right. Going to the right, we now have the multiply sign, shout it out, left, right. Left node goes to D, then right node goes to E. So the end of this process, we have shouted out every single node within this tree. And this is exactly what a traversal does. A traversal needs to visit every node in our tree exactly once and do something with that data. Here we did a traversal that's called a pre-order traversal. What we did is we shouted out our node first, and then we went to the left, and then we went to the right. It's called pre because that's when we actually did the shouting out. That's when we did the visit of the node. If we think about the source code for this, that simply means we need to print out the value of our node, and then after we print out the value of our node, then we need to do a recursive call to the left child and the right child. We can go ahead and write this code real fast. Here in a binary tree member function, we're going to do a pre-order traversal. And the first thing we're going to do is we're going to call a shout function. And that's going to happen on the current node. Then we need to call our pre-order of cur left and our pre-order of cur right. The final thing we need to do is we need to actually make sure we do a null check to ensure that we don't ever have a null pointer exception when we shout out cur or when we visit cur left or cur right. To do that, we simply add our null check around this entire function. If cur does not equal null, we run all of this code. Awesome. We have a pre-order traversal, and I think you'll be able to find out exactly how an in-order and post-order traversal works. But let's go ahead and check them out. Just like before, we have a traversal, and we've done pre-order, and now let's do in-order. In-order means we're going to go left, and then we're going to shout it out, and then we're going to go right. So line 52 has nothing, line 56 has nothing, line 54 does our shout out of our current node, and we're doing an in-order traversal. So we have the source code, let's run the source code. In-order traversal means we do left, shout right. So we've done left at the root node, so we move to the left, left at the root node, we move down here, left of A goes nowhere, so now we shout out A. The first thing we print out is A. Now we go back up, shout out the minus, and now we go into our right subtree, go left subtree. Here at B, we're going to shout out B because there's no left child. Then we go right, going back up to division, we shout it out, division, then go right and go into C, and we have A minus B division C.
Going back up to the root, we now have plus, shouting out D times E. So all I did was do an in-order traversal of every single thing, and look what we have. We have something that looks like a math equation. What we see is an in-order traversal in an ordered tree is going to be the exact order things go into. So this tree happens to be an algebraic tree where we have a math equation encoded in the tree. If we add parentheses for layers, then we can see that this code exactly shows us how we might go about encoding a math equation into a tree. The very last form of traversal is a post-order traversal. A post-order traversal is the exact same logic, except we're going to shout at the end. We're going to do left, right, shout. And that's going to be the exact order we visit every single node. What that means is the root node is going to be printed last, because it's going to visit the entire left subtree, the entire right subtree before shouting out the node. Let's do this real fast, just an example, but it flows exactly the same way as before. Again, the order is going to be left, right, shout, and this is going to be called a post-order traversal. And visiting plus, we go left, left. We get to A, we do left and right, and now A is shouted out. We then have visited left, we need to go right, left, right. Here's B we shouted out, and then C we shout out, division minus. Then we go to the right child, left child, D, E times plus. This is a post-order traversal of the exact same tree. So what you saw is we didn't vary the tree at all through this entire process. Instead, the only thing we did was change when we shouted out the node, either at the beginning, before the left and right, in the middle, in an in order, or at the end, in a post order. So these are the three most typical forms of a traversal that we see on a tree. But there's one more that is completely different. So you may not want to actually go into left and right subchildren. You may want a different form of traversal altogether. And for that, there is one special traversal that is widely used, and that is a level order traversal. A level order traversal is going to read every single level one level at a time. You're going to read the first level, then the second level, then the third level, left to right. Let's see an example of that. So a level order traversal is going to visit everything on the root level, then everything on the second level. So we see plus on the root, minus times, then everything on the third level in order, A, division, D, E, finally everything on the last level, B, C. This is a completely different way of visiting the exact same tree. Every single traversal we did had a unique ordering of things, but every single traversal we did visited every single node exactly once. There's one last thing I want to mention in this video before we finish it up, which is the idea of a traversal and a search, because often these terms are used interchangeably. Doing a traversal requires that every single node is visited. On the other hand, a search allows us to discover a particular node throughout the tree. So when we discover a node in the tree, we may not visit every single node. We may use a strategy developed in a traversal to help us find a node quickly, but a search ends as soon as we find that node, while a traversal is going to visit up to every single node. This is a broad overview of what it means to do a search and what it means to do a traversal, and different forms of doing traversals throughout the tree, which may influence the searches that we use later. We'll dive more into trees in the next video. I'll see you there.
A binary search tree is an ordered binary tree, capable of being used as a search structure. Let's see how this works. An ordered binary tree, or a binary search tree, is a binary search tree if and only if, for every single node, all of the nodes to the left side of a node is going to be less than any given root node, and all of the sides to the right of any given node is going to be greater than that node. What that means is we have the ability to recursively apply this definition. If we look at this node 19 right here, we know everything on the left side of 19 has to be less than 19. You see 4, 2, and 11 are all less than 19. Everything greater than 19 has to appear on the right side. 22 and 20 are both greater than 19. We can use this idea of a binary search tree to store a lot of data that we want to look up quickly. And often we're going to use a dictionary as our implementation structure of the binary search tree. What that means is we're going to implement a dictionary using a binary search tree. A dictionary is always going to associate some key with data. So for example, your email login is going to be associated with your profile data. So for example, if you log in with your email, then that email on Coursera is going to know exactly what all courses you're enrolled in and all of that data associated with you. Likewise, your phone number will likely go to your phone record at some phone company. A website URL is the lookup value. It's the unique key that gives you a particular website. And your street address is a unique value that tells the world exactly where your house is. All of these things take some unique key value and provides us some data that's associated with the key value. So here, the thing to remember are keys need to be unique identifiers. So keys have to be distinctive and unique, and they can't be the same as anyone else's key. So for example, a phone number is a unique identifier to your phone. No one else in the world shares your exact phone number. When we think about a dictionary, there are 4 key functions we're going to be building out. And those key functions are going to be, we want to be able to find data within this dictionary. So if we have your phone number, I want to be able to look up information about you given your phone number. When you log into Coursera using your email address, we want to make sure that that email address is going to be able to be looked up to your profile data, and only you have that email address. So find is going to take a key in and find the data associated with that key. The second function is there's going to be new users and new people getting cell phones. And that way we need to be able to insert more data into our dictionary. So when new data comes, we need to insert it. Likewise, we need to remove data that's no longer being used inside of our dictionary. So we need both an insert and a delete. And finally, the last part of the ADT is we want to know whether or not this dictionary is empty. We want to be able to determine whether or not we've deleted every single node. So when we draw a binary search tree, we're always going to be drawing just the keys, even though every node associates data with that key. So what this means is, here you look at the node 37. This node we're just going to draw as 37, but notice there's data associated with 37. Every single one of these nodes have data. We're never going to draw the data. It just kind of makes things clunky. But we're always going to be looking up by key and returning the data. So remember, at every point in time, you always have keys and you always have data. The implementation of the dictionary data structure is going to look very common to code you've seen already. In fact, it's going to look just like the trees that we implemented last week. What this means is that we're going to have some common functions up here in the public section, and our private section is going to contain a tree node class. Inside the tree node class, we're going to have the same left and right pointers that you've seen before. And now we're going to have both a key and a data as part of our values inside of the tree node. Here we see we have a tree node constructor, and we still have a head pointer that points to the top of this tree. So all of these things are just like a tree that we were introduced to earlier, but now we're going to do a dictionary class that implements a binary search tree that's going to allow us to make searches efficient. So let's think about how we can code an algorithm to find a particular element in the tree. So looking for the element 42, we're always going to start at the root. So starting at the root, we're going to look at the root element and determine whether or not we need to move left or right. 37 is greater than 42, so we need to move right to find where 42 may be located. Looking at 51, we find that 51 versus 42, 42 is less than 51, so it must appear in its left subtree. And finally, we found the node 42. So we start at the root. At each level, we determine if we move left or right until we find the node. Looking at a second example, we can run through the same tree looking for 11, again starting at 37, moving left to 19. 19 versus 11, we move left again. 4 versus 11, we move right, and we find the node 11. Suppose we want to find something that doesn't exist in the tree. Node 17, we can start again at the root, go left to 19, go left again to 4, and then go right again to 11. And now, 11 versus 17, 17 must appear in the right child of 11. Because we reached the end of the tree, we know that 11 is not in our data set. We know this because we reached a leaf in the tree and we can't go any further to search deeper. Once we've gone one path through the tree, following the rules every step of the way, if we reach the end and we haven't found the data, we know for a fact that that data is not in our data structure. even though we haven't searched the entire tree. Let's think about the very worst outcome of find. So if we think about a binary search tree, we may not find an element, and we may have to travel down the longest path in order to not find this element. So as we move through this longest path, we're taking a lot of steps looking through data. But notice we're not looking through all of the data. This is not as bad as an array or a linked list where we have to travel over every single piece of data. Here we only need to take one path through the tree. So the very worst case is going to be visiting the longest path. Visiting the longest path through the tree means that we are going to be visiting nodes proportional to the height of the tree. So using our big O notation, we have big O of h being the height of the tree as the worst case running time. The very worst case tree we might build might be a tree that looks like a linked list. So if we absolutely need this in terms of O of n, we can say O of h is bounded by O of n. So the very, very, very worst case is our tree looks like a linked list. It's not a very complete tree. It's a tree that simply has one long chain all the way to the left or all the way to the right. This one long chain is going to have a path length that's going to be equal to the number of nodes in the tree, and the height is going to be proportional to the number of nodes in the tree. So the worst case running time in general terms is going to be the height of the tree. The worst case running time in specific terms of data without knowing anything about the structure of the tree is going to be O of n. Let's look at the code that will actually run this algorithm. So here we have two different functions. The first function we're going to have is a find function. This find function is simply going to call our helper function, passing in the key and the head. So we're going to start at the head or the root of our tree. And then once we've done that, we can look at our helper function find here, and we see we have four cases. If the current pointer is null, we go ahead and return that current pointer, so we return null pointer. If our current key is equal to the key we're searching for, we can just return the current node because we found it. If the key is less than the current key, we move left. If the key is not less than the current key, we move right. So this is all we need to do. All we have to do is simply start at the root of the tree and traverse through the tree, going left or right based on the comparison of the value to my key. And then once we found our data or found the end of the tree, we simply return that node, being the data itself or a null pointer. And you'll notice here the very last two lines of code, lines 21 and 22, we simply say if we found null, we're going to throw an error. Otherwise, we're going to return that data. So we know how to find a tree. Let's talk about how we might insert into a binary search tree. So inserting into a binary search tree should be pretty simple. All we need to do is find the exact location it should be inserted at and insert it there. So looking for 17, we use the find algorithm we just discussed. Starting at the root, 37, going left to 19. 17 is less than 19, going left again to 4. 4 versus 17 means we need to go right. 11 versus 17 means we need to go right. And we've actually found the exact location we want to insert into the tree because we've reached a leaf node. 11 doesn't have any children to the right. And now we can add 17 right here, and we maintain the binary search tree property. And as soon as we search for 17, we're going to find it right where we inserted it. The insert algorithm is trivial because we're able to use the fact the find algorithm returns a pointer by reference to the exact location where we need to insert at. So here the two-line implementation is let's use our find function to find the exact position that we should insert into the binary search tree. And let's just go ahead and set that position, that node that we're returning, equal to a new tree node. That's it. That is the most elegant implementation we can do to insert, only 2 lines long. We're almost done here, but there's one more algorithm we need to talk about, and that is the idea of removing. So we have the ability to find, we have the ability to insert, and now let's make sure we have the ability to remove. So here we're going to remove the element 42. Let's see how this would work. Let's use the same find function we've used all along, and we go right, left, right. Here we found 42. It's really easy to remove 42 here. We can simply wipe away this link and node, setting this pointer equal to null, and we have a binary search tree that's still built completely acceptable, completely correct, and we've deleted the node. It's just like removing from a linked list. So this is a particularly nice case to find. Let's see if we remove another element if we get trickier. So let's remove 22. 37, moving left to 19, moving right to 22. Yikes, so we can't simply remove 22 because we lose track of 20. But this again looks like a linked list. If we consider the fact that we just have nodes linked together like this, we know exactly how to repair this because we've repaired a linked list. Instead of simply deleting everything at this pointer and setting it equal to null, we delete the node and repair it by moving this pointer to the one child. So in the case of a one child remove, I'm going to argue that this is an easy case because this looks like a linked list that we already know how to remove from a linked list. Now there is a case that you're probably thinking about. What happens if there's a two child remove? We can't simply update it like a linked list because we don't know how to deal with both a left and a right child. Let's see an example that does this. We've removed two elements from this tree, and now we need to remove 37. We again start at the root, and here at the root, oh, we found our element already. We are removing the root node from the tree. This is probably the most difficult node to remove. So removing this node means that we need to go ahead and think about a strategy to remove it. If we simply remove it altogether, we would then need to either decide if 19 should be the root or 51 should be the root, and then how we repair this tree is going to get extremely complicated. There's going to be lots of edge cases depending on the structure of the tree underneath, and it's going to be far more complicated than just thinking about a more generic algorithm that's always going to work. So if I think about 37, if I were to remove the root of the tree, what is the best candidate to be placed at the root of the tree? Well, the best candidate is probably going to be the node that is best suited to be at the root position of the tree that wouldn't disturb anything else about the tree. So thinking about all of these nodes, the best node to replace 37 is going to be the node that is closest to 37, either less than it or greater than it. So 37 and 20 is the best node in this left subtree to replace 37. So imagine this is 20 and everything else remains the same. Given this element is now 20, 19, 4, 2, and 11 all sit on the left-hand side. This looks good. 51 and 55 all sit on the right-hand side. So this is sane. This is correct. We'll actually quantify this into an algorithm. We'll say that we are going to replace the root of the tree with what we're going to refer to as the in-order predecessor of a given node, or the IOP. So the in-order predecessor of a node is going to be an in-order traversal of our binary search tree, such that we choose the element that appears immediately before the root. So the root is 37, so the in-order predecessor is going to be that element 20 when we do an in-order traversal. We can also develop a clever way of finding the IOP. The IOP is always going to be the rightmost node in the left subtree. So if we look at our root node that we need to remove, and if we go into its left subtree, then we simply need to find the rightmost node in that subtree. So the rightmost node in the left subtree is going to be the greatest value inside of the left subtree. So we find 20, we swap it with 37, and by swapping that 20 with 37, we are going to find that we can build up a binary search tree that is correct without worrying about any particular edge cases. The last little bit is when we do swap 37 with 20, we still need to remove 37 from the tree. We still have this node right here, but when 37 has been swapped with 20, we know that 20 is the rightmost node in the tree, so therefore it must not have a right child. So it must either be a 0 children remove or a 1 child remove. Given that it's either going to have 0 or 1 children, we can effectively remove it using one of the two cases we discussed earlier. So to summarize, when we remove from a binary search tree, we have 3 different special cases we need to consider. We need to consider the case where there is 0 children to the node we want to remove. That's going to be simple, and we simply delete the node because there's no children underneath it that we have to worry about keeping track of. In a 1 child remove, we have a structure that looks like a linked list. And given a linked list, we already know how to remove an element from a linked list.
So we don't have any concerns about repairing that linked list by simply setting that pointer equal to the next element. Everything's going to be totally fine if we just have one child. The two children case is interesting. We need to find the IOP, or the in-order predecessor. We need to swap the node that needs to be removed with the IOP, and then we need to remove that node in its new position, which will either be a case of a one-child remove or a zero-child remove. So we have this algorithm that's somewhat recursively defined in the sense that we're swapping something and then removing it using that same remove algorithm. But by doing that, we're guaranteeing that this swap is going to be an easier case. So let's go ahead and look at what the implementation remove looks like. Just like all of our functions that are going to run recursively on this tree, we have a remove function that's going to be publicly available to the client. It returns data by reference. And the tree node is going to use our find algorithm to find exactly what node should be removed. And then we'll call remove to remove the node we found. Here in the dictionary, we're going to do remove. And we have the zero-child remove case, which just removes the node directly. We have the one-child remove case, which I split up into the left child and the right child. And you'll notice the code's identical except for swapping whether or not we go left or right at one given location. We're simply looking at the data and repairing the linked list based on whether or not there's a left child or a right child. And then the very final case is going to be straightforward. We find the IOP, we swap that node, and we call that remove function on the node that we just swapped at its new position. So I've set up a little program that we can actually run and see how this code works and get some output in it, and you can dive in and kind of edit and play around with this code. So let's go over to the console and see how this works. Going to our console, we can move into the binary search tree directory and run make. After make finishes, we can go ahead and look at the code that we're about ready to run. Here in our main.cpp, we create a dictionary based on what we just discussed, and we insert a number of elements in that dictionary: 37, 19, 51, 55, 4, 11, 20, and 2. Notice the data associated with all of these elements are going to be strings that say the exact value of that element itself. Then we run several operations. We find 51, we remove 11, 51, and 19, the 0, 1, and 2 child removes that we did. And then finally, we're going to try and find 51 again and see what happens after we've just removed 51. Let's go ahead and run this by running /main. T.find of 51 finds the element 51, exactly what we expect. T.remove 11 removes the element 11. Remove of 51 removes the element 51. 19 removes the element 19. When we find 51 again, notice that we aborted. We had an exception thrown, and it says uncaught exception have found runtime error, the key's not found. Because we could not find 51 after it's removed, we saw an error happen. This is exactly what we expected the code to do, and we have a working binary search tree that you can play around with, and you can mess with that code. So I hope you can play around with that code, and then we're going to do some analysis on exactly what's happening in this binary tree in the next video. I'll see you then. Binary search trees can take on many different forms and structures, even if they contain the exact same data. Consider these two binary trees. Both of these binary trees are correct binary trees in the sense that the left side always contains nodes less than the root, and the right side contains nodes only greater than the root. Both of these contain the numbers 1 through 7. They're both correct binary trees, but they have a very, very different structure. So these two trees, as I mentioned, contains all of the same values. And the way we built these trees was by varying the insertion order of the trees. Here, I built a tree by inserting 4, then 2, then 3, 6, 7, 1, and 5. By doing that, we create a tree that is perfectly balanced. The number of nodes on the left side is equal to the number of nodes on the right side. On the other hand, I created a tree that we have nodes that are entirely balanced to the right. The root node ended up being 1, so everything is going to be greater than 1, and everything's going to be on the right side of the tree. So we want to think about how can we build trees that are both efficient
and what happens when we build a tree that's not so great. What is the average case? What is the worst case? And what's the very best we can do? So let's think about how many possible ways there are to insert data into the same binary search tree. So if we have the numbers 1, 2, 3, 4, 5, 6, and 7, we can think about how many possible ways we can insert. So this is a pretty simple puzzle in the sense that we can just choose one of them and say that's going to be the first number we insert. So let's say we insert 5. By inserting 5 first, we know that 5 is going to become the root. At that point, we have the choice of 6 other nodes to insert second, and we can make any choice here. We could choose 2. Because the first choice we made was a choice of 7, the second choice we made was the choice of 6 nodes. The next choice we'd make is the choice of 5 nodes. Then we have a choice of 4 nodes. So the number of possible ways we can insert the exact same data is going to be equal to 7 factorial, or the number of nodes in our data, n factorial. So there are n factorial different ways to insert the exact same data into a binary search tree. So what that means is we know that there's a whole slew of different possibilities of how our binary search tree might be structured. In the very worst case, we know our binary search tree may just be a linked list with the smallest node at the root, and we increase in increasing order. So if we insert it by 1, 2, 3, 4, 5, we can see that that tree is going to look like a linked list that's going to move to the right at every single position. So if we need to find a node in that worst case binary search tree, we're going to see it's going to take order n searches through that data. So every single element of that data is going to be searched. This is the exact same thing as searching through a linked list, because in a linked list, we can't skip any elements. So we're stuck with this order n runtime. On the other hand, a sorted array has the ability that we can jump directly to the middle. So as we discussed in arrays, we can access any arbitrary element. In a sorted array, we can say if all of the elements are in this array and they're in a sorted order, then we can just simply jump to the middle of the array and say, okay, 3, is that data acceptable? Is that data the data I want? Maybe. If not, I can move left if it's less than that, or right if it's greater than that. So we see that this is going to be a logarithmic running time. So this is going to be order log n. And we find that the average case of a binary search tree is going to be a binary search tree that is pretty well balanced. If we think about all of the possible ways we can insert into a binary search tree, only one of these ways is going to result in a tree that leans directly right. Only one way results in a tree that leans directly left. On average, half of our data is going to be to our left, half of our data is going to be to our right. So an average case binary search tree is just like a sorted array in log n time. Remember that all of our operations depend upon find. So when we're finding an element in a binary search tree, we insert it by just adding one more line of code. We remove it by just considering 4 particular cases that in itself only call find. So we find for a binary search tree, the running time of find is going to be the running time of both insert and remove, because insert and remove only do constant time operations after finding the element. On the other hand, a sorted array, we've discussed the idea that in an array, it has to be contiguous memory. So if we insert and remove from an array, this is going to be O of n time. And from a sorted list, we have to find the element, so we have to spend the time to find it, and then we can insert quickly. The best outcome, the only algorithm that runs in log n time for both find, insert, and remove is this average case binary search tree. We can't do that with an array. We can't do that with a sorted list. Both of these have some runtime that's going to run in O of n time. Because of that, we really would love to be able to get to this average case binary search tree. That's going to be the gold standard we're aiming to. But this worst case is going to be the very worst case. Notice that this O of n is true for every single operation and will never help us outperform an array. To help us start to quantify what it means to have a balanced binary search tree, let's define one new term. This term is going to be the height balance factor, or B, of a node. This height balance factor is going to be the difference in height between the left subtree and the right subtree. So B is going to be equal to the height of our right subtree minus the height of our left subtree. So here the height of the right subtree is going to be 1. Here's the height of the left subtree is going to be 1.
1 minus 1 equals 0. So we say the balance factor of this root node is 0, that this node is perfectly in balance. On the other hand, if we look at this tree, we can say the height of our left subtree is the empty tree. So we define that height to be -1. And the height of the right subtree is going to be 1, 2, 3, 4. So 4 minus -1 is going to be equal to 5. So we say the balance factor of this tree is going to be +5. This means that this tree is heavily swayed to the right, that the right has a height difference of 5 compared to the left side. Ideally, we want to keep that balance factor small. And let's think about how we can actually do that. We're going to define that a balanced binary search tree is going to be a binary search tree where every single node in this tree has a balance factor with a magnitude of either 0 or 1. By having a magnitude of 0 or 1, that means the balance factor can be either -1, 0, or 1. Only if these three are the only balance factors that appear in every single node in the tree do we say this binary tree is balanced. So here, this left tree, every node's going to have a balance factor of 0, so we're in great shape. Here, this node 6, this has a balance factor of 0. Left and right trees are balanced. This node 7 is going to have a balance factor of -1. So this subtree right here is in balance. This subtree is fine. The subtree becomes out of balance once we get here, when the node 5 has a balance factor of 2. Notice that the right side of the tree has a height difference of 2 compared to the left side of the tree. So here, this tree is out of balance. Obviously, it gets more and more out of balance the further we go up. Balance factor here is 3. Balance factor here is also 3. And then the balance factor of this root node is 5. So there's n factorial different ways to create a binary search tree with the same data. The worst case binary search tree will be a binary search tree that mimics a linked list as a long string of nodes. The average case, though, will be a tree that's height is proportional to a logarithm of the number of nodes, that it's going to be a relatively balanced tree. We're able to quantify the idea of balance by defining a balance factor which determines a height difference between the left subtree and the right subtree. We define a balanced binary tree to be a binary tree where every single node has a balance factor of either -1, 0, or 1, or we say the magnitude of the balance factor is no greater than 1. In the next video, we're going to dive into understanding how we can create an algorithm that maintains the balance of a binary search tree. So I'll see you then. In the last video, we talked about the balance factor of a binary tree. Now we're going to talk about the balanced binary search trees, which are trees that are height balanced to ensure that nearly half the data exists on the left half of the tree, nearly half the data exists on the right half of the tree. Here on the left, we see a very balanced binary search tree, while on the right, this binary search tree is far out of balance. Let's analyze substructure of this tree and develop an algorithm to ensure that we can turn a binary search tree that's unbalanced into a binary search tree that's completely balanced. There's two substructures that we're going to identify in a graph. We're going to identify a substructure that we're going to call a mountain, which is a node that has both a left and the right child, and a substructure called a stick, which is going to be a node that has two children in the same direction and no children in the other direction. The stick is going to be something that we're going to want to transform into a mountain. By transforming sticks into mountains, we're going to make sure that our binary tree stays as balanced as possible. So let's consider a binary search tree and a pretty simple example. This binary search tree was initially balanced. We know it's balanced because we can check the balance factor of every single node, which is the height of the right child minus the height of the left child. Height of the right child in this original tree is simply going to be 1. The height of the left child is 0. And doing 1 minus 0, we see the balance factor of the root node is 1. By adding a new node to the end of this tree, now the height of this right subtree is 2. 2 minus 0 is 2. And because the magnitude of the balance factor is greater than 1, we know this tree as a whole is out of balance. So when we look at this tree, we want to consider where the deepest node that is out of balance. So here, this new node added, it has a balance factor of 0. We have the same number of children on both sides. Its parent has a balance factor of 1 because it has 1 extra height on the right side over the left side. Next tree has a balance factor of 1. Again, left side having a height of 1, right side having a height of 2. Only here at the root node do we see that the balance factor is 2, and that's the deepest point in the tree that we're out of balance. Once we've identified the deepest point in the tree, we're going to identify the stick that causes the node to be out of balance. Here we've done just that. Notice the stick running from U, V, and an unlabeled node is 3 nodes that make a stick that is the reason this tree is out of balance. Let's try and transform this into a mountain. To do that, I'm going to pick up the middle node in the stick, right here, this V, raise it up, and by raising up this middle node, by pushing this whole node up, we see that this node is going to become a mountain. And this mountain, then we simply repair all of nodes. Notice to the left of U, there's a pointer. To the left of U, there's a pointer. The node that was off the left of Y is now going to be on the right of U. And the right of Y is going to be untouched. So what we've done is we have created a tree that's going to maintain the factors of being a binary search tree. So all of the order here is maintained, and we've decreased the balance factor of the root node. So here, now the balance factor was 2, and you've transformed it into a balance factor of 0 through using a simple binary search tree rotation. So if we consider this arbitrarily, we can talk about generic left rotation. The idea of a left rotation is we're going to consider the deepest point of the tree that has an imbalance to be node B. So here, right at the top, this is the node. This may be somewhere deep inside the tree. All we know is this node B is the lowest or deepest point inside of our tree where we've detected an imbalance. An imbalance is a balance factor that has a magnitude greater than 1. So here the balance factor is 2. When the case the balance factor is 2, we need to look at this next node. So we look at C. Given that we found B, we now look at C and see what the C's balance factor is. If C's balance factor is 1, we know that B is out of balance heavily to the right, and C is also almost out of balance to the right. That means our tree definitely has a terrible slant to the right. What we can do is we can do what's called a left rotation to solve this. Doing a left rotation, this means bringing C up and making it tip of the mountain and rotating everything to the left. That brings B down and attaches C to B. So looking at T1, T2, we see T1 and T2 is attached to B, C is attached to B and D, and finally T3 and T4 remains attached to D. We call this rotation a left rotation, and this rotation occurs whenever the deepest point of imbalance has a balance factor of 2, and the balance factor of the node that follows has a balance factor of 1. Anytime this occurs, we can do a left rotation to repair this imbalance. Let's consider a second example. This is going to be very similar, but instead of having a node added to the left, we have a node added to the right. If we identify the substructure that has the problem, the deepest point of imbalance is now here. It's no longer the root node, but this node has a balance factor of 2. Notice that the height of the right subtree is 2. The height of the left subtree is 0. 2 minus 0 is equal to 2. This unfortunately doesn't fit our cases that we've looked at so far. Instead, we've identified a structure that looks more like an elbow than a stick. And this is indeed our third structure. This is sort of a hybrid between both a stick as well as a mountain. What we need to do whenever we identify an elbow is actually to fix the elbow to make it a stick. We do that by doing a rotation about the bend of the elbow. Notice here, we have an elbow. We do a transformation by moving the yellow node up. This yellow node up then transforms this elbow into a stick. Once we have a stick, we know exactly what to do. We consider this a right-left rotation because what we're going to do is we're going to do a right rotation about D to place it in place, and then a left rotation about C to fix the stick. So here, this right-left rotation is going to be required whenever we identify the point of imbalance in the tree B, the balance factor of B is 2, and then the balance factor of the node that follows B is going to be -1. An insert at T2 or T3 is going to cause this point of imbalance, and we simply need to do 2 different rotations to fix this imbalance. Seeing this completely, we notice that we first transform this elbow into a stick, and once we've transformed the elbow into a stick, we raise up the center node of the stick and make it into a mountain. So here we go from an elbow to a stick into a mountain. And at the end, we notice we take a tree that's completely out of balance and have a nice, perfectly balanced binary search tree at the end of this process. So we can look at all of this rotations and think about how we can just flip this idea that when we have a left rotation, if we consider a tree to be out of balance entirely opposite direction, we simply need to do a right rotation. Looking at a balance factor of the deepest node of imbalance in our tree, if it is 2, we start with a left rotation. If it's -2, we start with a right rotation. Only then when we look at the next node, can we identify whether or not it's a single rotation. So if both of the signs match, we say we only need to do a left rotation. This transforms a stick into a mountain. Just like negatives, we transform a stick into a mountain. When the signs differ, we know we have a case of an elbow. When we have the case of an elbow, we need to do a double rotation, or a left-right rotation, or a right-left rotation. This unbends the elbow and then does the simple transformation to transform a stick into a mountain. So I introduced these things in really simple terms, so we can talk about sticks, mountains, and elbows. And we saw visually how this code is able to transform an out-of-balance binary search tree and bring it into balance at the moment we detect the imbalance. So as we insert nodes, we're going to want to ensure that we're keeping the binary search tree in balance every single insertion. And when we complete an insertion, we're going to ensure that by the time we return it back to the user, that binary search tree is going to be balanced. BST rotations, or binary search tree rotations, is the mechanism to restore that balance. We know there's 4 different rotations: a left rotation, a right rotation, a left-right rotation, and a right-left rotation. These rotations are all local operations. All we're doing is changing the point of imbalance, rearranging a few pointers. Because of that, we can say this runs in constant time. The code we're going to write to do these transformations are going to be as simple as 4 lines. The last thing to mention is this algorithm actually has a name. This is called an AVL tree. We're going to dive into all of the details about an AVL tree and talk more about it next lecture. I'll see you guys then. Balanced binary search trees are kept in balance through tree rotations when we do an insert and remove. We call these trees AVL trees, named after 2 computer scientists, Adelson Velsic and Landis. An AVL tree is just like a binary search tree. Everything you know about a binary search tree still holds true. That includes finding, inserting, removing, and everything else. We only do 2 things differently in an AVL tree. That is, we do some extra work on insert and remove to ensure that we keep the trees in balance. And to keep the balance factor to be able to be computed easily, we're going to store the height of every single node in the tree. We'll see how this works through examples. So let's go ahead and look at an insert. Suppose we want to insert the node 14 into our binary search tree, or an AVL tree. Just like the insertion algorithm we talked about previously, we're going to start at the root, compare 14 to 18, and find that we need to move left. Looking at 5, 14, we need to move right. 10, we need to move right again. 12, we need to move right again. And here we can insert 14 as a new leaf node right at the end of this path. We do this insertion through a recursion algorithm, so we can always check each thing as we move back up the tree. So let's actually look at a stepwise process for doing this. The first step is to insert at proper place. We know that the insertion happened by taking this path right here and inserting here at 14. As we move back up the tree, we're going to check at every single place for an imbalance, rotate if necessary, and update the height. So here, the height of 12 is now going to be equal to 1, since we have 1 node below it. Moving up to 10, we see the height of this element is going to be 2, because we have 2 nodes below it. But what happened here? We have an imbalance right here. We have one side of the tree, the right side, having a height difference of more than 1, specifically a height difference of 2. So we know that this tree is out of balance right here. So we need to go ahead and repair that. We do that through a simple rotation. We're going to have 12 moved up. So 12 is going to be the top node, 10 is going to come from the left, 14 is going to come from the right, and we have a repaired binary search tree. The height of 12 is 1, the height of 10 is 0, the height of 14 is 0. And now we can move up to 5, check if 5's height is still 3, it is, and then check at 18, height is still 4. So by doing an insertion and moving back up the chain, we saw we only need to do a rotation somewhere along the path we took to do the insertion. We found we had to do one rotation this time, but we were able to insert 14 and ensure that the AVL tree was a balanced binary search tree by the time we gave it back to the user. The code to ensure the balance was added to the binary search tree code you saw last lecture, and now we have this extra helper function called ensure balance in our AVL tree. This ensure balance function is going to help us by ensuring that if our balance has a value of -2, we know that we need to either do a right rotation or a left-right rotation. If our balance is 2, we know that we need to either do a left rotation or a right-left rotation. We determine that by looking at the balance of the next node. So here we see the height of the cur left-right and the cur left-left. This is exactly what we saw in the diagrams that we looked at previously. So everything you saw in the last video and this video came together in this function to ensure that if our tree is ever out of balance, that we do the proper rotation based on a table we discussed last time to get the tree back in balance. Taking a look at the rest of this, we need an update height function that simply updates the height and a rotate left function to do the actual rotation. And that's it. The only other place we need to do actual work is in remove. So let's look at the possibility of removing 5 from our original binary search tree. Here we're going to find 5 just as we've done before. 18, move left to find 5, and we found the node we need to remove. Remember, to remove a node, we need to find the in-order predecessor of that node. That means we have to find the node that comes just before that node, or the rightmost node in the left subtree. The rightmost node in left subtree is going to be the element 4, so we go ahead and swap 5 with 4, and then we need to remove this node we just swapped. So we remove 5. We'll notice that we now have, as we move up this tree from 5, we have to rotate 3 because 3 is now out of balance. There's a height difference of 2 on the left and the right. Rotating this, we're going to see that it's an elbow. So the first thing we're going to do is transform the elbow into a stick, and then we're going to raise the middle element of the stick so that we now have 2, 1, and 3 hanging off the left side of the 4 element. Now we see that with these, with a height of 1 here, and a height of 1 on the left-hand side, and a height of 1 on the right-hand side, the middle element here has a height balance exactly right. The height has actually shrank slightly, so the height is now 2 here. We move up the tree, and we see the height of the root is 3. So just like before, the only nodes we have to update is the path we took to do the deletion. When we remove an element or we insert an element, we only need to modify nodes along the path to do so. So the code to modify the remove is just going to be simply adding an extra function called IOP remove that's going to go ahead and remove the IOP, and it's going to find whether or not where the IOP is by looking at the rightmost pointer in the left subtree. And if we have found the IOP, we're simply going to swap that element and then going to go ahead and call our remove function to remove it altogether. You will have all this code provided for us, and we'll take a look at it in a second. So as a reflection on all of this, we know that an AVL tree is an implementation of a balanced binary search tree. And an implementation of an AVL tree starts with a binary search implementation and then just adds 2 things. We added the height of every single node to be stored with the node itself, and we maintain the balance factor of the tree after every insertion and remove. By only doing those 2 things, we ensure that we have a balanced binary search tree. So before we go, let's take a look at the code, and then we'll discuss exactly how this AVL tree runs in our next lecture. So let's look at some code.
Going to the AVL directory, I can check out what's in main.cpp. You'll see inside main, we create an AVL tree. This AVL tree is going to be a dictionary where we have integers as the keys and strings as the values. Here we insert a number of things in an AVL tree, just like we did in a binary search tree. The key is going to be the integer number. The value will be the string itself saying the integer number. And we'll see out a bunch of things. The first thing we're going to do is we're going to find 51 using the code we have for our AVL tree. Then remove 11, 51, and 19, as well as 6. So 11 is going to be a simple remove where there's no children. 51 is going to be a somewhat simple remove where there's 1 child. And then 19 and 6, those are going to contain 2 different children in our AVL tree to make them more complex moves, to make sure that we handle the IOP situation exactly correctly. The very last thing, we're going to find 51. We expect to have that to be an error because we just removed 51 earlier. Let's go ahead and run this and see what happens. Running make to compile. And then /main. We see when we find 51, we indeed get the 51 value out. Removing 11 removes 11. Removing 51 removes 51. Removing 19 removes 19. Removing 6 removes 6. Here, when we find 51, we find that we have an uncaught exception, key not found. This is exactly what we expect, because since the first time we found 51, we've removed it, and now 51 no longer exists. So you have the source code for the AVL tree. You have all of this information. You can play around with doing amazing things with the AVL tree yourself, and I hope you'll spend some time doing that. So have fun, and I'll see you next time. Up until now, we've discussed algorithms such as binary trees, AVL trees, arrays, and lists, and they have incredible runtime performance in terms of big O notation. But big O notation doesn't explain everything. In fact, big O notation assumes a uniform access time for all of our data. But in reality, uniform access time for all of our data isn't actually the case. Let's look at an example. For example, if we consider all of the Facebook profiles on Facebook, we might give a conservative estimate that there are 500 million users on Facebook. Sure, there's more than that. And let's think about every single Facebook profile. We might imagine that the total amount of data that's on each profile is going to be at least 5 megabytes. Again, another conservative estimate, because likely all the photos and all of the information we're storing on Facebook is probably going to far exceed 5 megabytes. Thinking about the entire amount of space that it would take to store all of this data, we can multiply 500 million by 5 megabytes. Doing that's going to result in us having 500 billion times 5 kilobytes, 500 trillion times 5 bytes, and then moving this over, that's going to be 2,500 trillion bytes, or 2.5 petabytes of data. This is an incredible amount of data. 2.5 petabytes of data is far more than you can store in any main memory on any system. So we're going to have to store some of that data on disk, and by storing on disk, we know that that operation is going to be somewhat slower than in main memory. The goal of a B-tree is to create a data structure that's going to perform extremely well in both main memory as well as in on disk. Specifically, we want to optimize the idea that we want to make as few disk seeks as possible so this algorithm can be as optimal as possible. And in fact, I said the term disk seek, but what we really can think about is anywhere the data is stored somewhere else. This might be on the cloud somewhere, or this might be anywhere else. So let's look at how we might construct such a data structure. A B-tree is constructed by having a node that contains a number of keys. I'm going to draw a node as simply a large rectangle. And as part of this node, we're going to have several keys inside of this node. And the keys can be any value. I'll assume that we're going to have integers here in the beginning. The first key might have the value of 1. The second key might be 100. Then the value 250, 400, 900, and 1600. Each of these keys are going to have a pointer to another tree node inside of it. So between 100 and 250, this pointer right here is going to contain another node that's going to have another set of keys. Everything in this node is going to be between the number 100 and the number 250. We're going to define every B-tree as having an order. The order of a B-tree refers to the size of the nodes, not the fact that the keys are in sorted order. The order of the B-tree is the maximum number of keys that a given node can have, plus 1. So for example, here's an example of a B-tree of order 9 having 8 keys in this node. The goal of every single B-tree is to minimize the number of network packets, disk seeks, or whatever operation we have to get at the data. So we want to minimize the seeks to reach our data. So now that we understand the motivation of a B-tree, we want to actually understand how we can implement it and how we can build operations like insert and find in this B-tree. So we'll do that next lecture, and I'll see you then. A B-tree of order m is a data structure that we introduced earlier that's going to optimize an algorithm for having a minimum number of disk seeks or network seeks to get at our data. A B-tree of order m is specifically a tree that contains nodes of order m. each node can contain no more than m-1 keys. There can be a pointer on the left and right of each key of the node, potentially resulting in m children because there are m total pointers coming off of that node.
And we talk about this data structure as being a B-tree of order m. Inside of a B-tree, we're going to start with just having a single node that has a number of keys inside of it. Let's imagine we have a B-tree of order 5. Having a B-tree of order 5 means that we're going to go ahead and insert elements into this tree. So for example, the element 14, 19, 42, 47, and 81. Inserting 14, we simply can put 14 into this key. 19 can go in here. We'll stick 47 in next, and then 81. Given a B-tree of order 5, we know that when we reach this point, we can't stick any more data in our root key node. Instead, we need to go ahead and, when we insert this value, create a new node that's going to contain this value. Let's see how this works. Looking at node 42, we need to stick 42 right here in the middle. But we can't do that because that's going to exceed the capacity of this node. Instead, how we do an insertion in B-tree is we need to throw up
The value 42.
to ensure that we have a new node. Think about entering 42 here.
We can then take the middle value,
Make 42 a new node. Everything to the left of 42, which is 14 and 19, can go on the left node. Everything to the right, the numbers 47 and 81, can go on the right-hand side. Now we have a B-tree that contains 5 values.
there are 2 keys in the left child node, 2 keys in the right child node, and the root node contains 1 key with the value 42.
The recursive idea of B-trees also holds. Let's look at this B-tree right here. That's a B-tree of order 3. Here, every single node is full, and we have multiple layers. Suppose now we want to insert the number 30. Inserting 30, we can go ahead and do a find in our B-tree. What this means is we're going to go ahead and say 30 is between 23 and 42, so we're going to advance this middle node.
And now, between 25 and 31, we'd place 30 to make this a node with 3 keys. But since the node has too many keys, we need to go ahead and throw up the middle value.
Here we see the middle value 30 is going to be brought up to the parent node. The parent node is now going to have the values 23, 30, and 42, with pointers that point down to -3, 8 is the left node. Here just 25 is to the left of 30. To the right of 30 is 31. Then 42 has the same right child of 43 and 55. Since this root node is now full, we need to again throw up the middle value. Here we can do this by bringing 30 to the top. The left of 30 is 23. The right of 30 is 42. And you can see the keys otherwise stay the same. 23 still has connected, and 42 still has 2 children connected to it.
Here we've seen the recursive nature of going down a B-tree to find the insertion point of a value, and then, only if the node is full, splitting that node in half and throwing up the middle value to the parent node until we find a node that hasn't been filled to capacity.
So we have this understanding of exactly how this algorithm works. And now we can look at properties inside of the B-tree itself. Looking at the properties of the B-tree itself, we can determine 4 things that are going to be true. The first thing is that we know that every B-tree is going to have keys that are ordered within a given node.
Remember that the keys being ordered means that they are in sorted order, which is a different meaning of the word when we say a B-tree is of order m. In addition to having ordered keys, every node has no more than m-1 keys.
But we're going to look at internal nodes as well. So every node internal to a tree, which means that every node that is not a leaf node, is going to have 2 properties. That is that there is going to be 1 more child and key for every single internal node. The idea being here that you have pointers on the left side and the right side of our array and pointers between every single element.
So we have 1 more pointer than the number of keys in the node.
That means it contains 1 to m-1 piece of data, since our array has data on both the left and the right side. So 1 piece of data is going to have 2 children, a left child and a right child. M-1 piece of data going to have m children.
We know that the root nodes are always going to have somewhere between 2 to m children.
And finally, every non-root node is going to be bound by having somewhere between the ceiling of the order m divided by 2, so somewhere between ceiling of m over 2 and m children. So every node inside of our B-tree is going to be at least half full. This makes sense because we're only splitting nodes as soon as they become full. So the result of a split node is going to be two nodes that are exactly half full. So we know the bounds in these nodes are always going to be between m over 2 and m. The last thing to mention are all the leaves in a B tree are always going to be on the same level. The way we construct this tree means that we're never going to have leaves that are on different levels. So a B tree is always going to have the same height no matter which path you take down the B tree. Here's an example B tree. We can talk about different factors of this tree. Here I haven't labeled exactly what the order of this B tree is. Instead, we want to do some analysis to figure out what the order of this tree is. Looking at this tree, we can see that there are some interior nodes
that have just 2 keys, and therefore 3 children. We can see that there's a leaf node that has 4 keys. Because this leaf node has 4 keys, we know that the order of the B tree must be at least 5.
Given that we have 3 children here,
We know m must be at least 3. And since we know the internal nodes is between m over 2 and m children, we know that m over 2 is at most 3, so m is at most 6.
we know the order has to be bound somewhere between 3 and 6.
Given these 2 criteria, the order must be greater than or equal to 5 from our first criteria, and from our second criteria that the order must be between 3 and 6. So the only condition that satisfies both these criteria is that the order of this B tree must be either 5 or 6.
Given that these are the 2 possibilities, and given the fact that B trees generally are splitting nodes, so it's nice to have odd values, this B tree was created as an order 5 B tree. And you should be able to look at any B tree and reason something like this. So what we've seen is we've seen a broad introduction of how to find a node in a B tree, as well as how to insert that node to create a larger and larger B tree. You saw the recursive nature of this, where we find a spot to insert, and then once we found the insertion point of the B tree, we're going to recursively run this algorithm so that we keep throwing nodes up higher and higher in the tree. Next, we'll dive into some analysis of the B tree, as well as some properties of exactly how much you need to search to find any given node. I'll see you then. At this point, we have a deep understanding of exactly what it means to have a B tree. Now let's do a little bit of analysis on what's happening. Here I have a simple B tree that's of order 3. And here we know that when we search for a node in this B tree, we're going to be comparing at each level one particular set of nodes, and we're going to need to do as many comparisons as is the height of this tree. Given that many comparisons, we can look at the code to actually go about doing this, and the analysis of how long this is going to take from a runtime perspective. Let's look at some code. Here in this slide, I have some code that you have provided as part of the GitHub code for this course. Here we can see that there's some interesting bits about this program. The first bit is we have a function on whether or not this key exists in our B tree. We take in a B tree node as well as a key, and this is a recursive definition. The first thing you'll note is we're going to search through the actual node itself using a linear search to check the point where we have keys equal to, or we find that we're past the key that has the value we're looking for. Once we know that we're past that key, we exactly know what child to move into. You'll see the next lines move into that child, and unless we find an exact match. And then after that, we ask if it's a leaf node. If it's a leaf node, we didn't find it. Otherwise, we move into the next child by using this fetch child operation. The fetch child operation is going to go out to the internet, or go out to the cloud, or go out to the disk, or go out anywhere to find that next child. And that's going to be the really, really slow operation. There's 2 interesting things about this code. The first is up here at the top of this code, you'll notice that the search we're doing is actually a linear search. Even though our data is sorted, we could do a binary search here. It would be totally fine to do that. But instead, we're just doing a linear search because the time comparison it takes to run this O of n algorithm here doesn't actually matter, because the time it's going to take to actually do the work is going to be significantly greater when we need to fetch a node. Because the fetching of a node is such an important part of this algorithm, we want to actually understand how long does it take and how many fetches are going to be required. The height of the B tree is going to determine the number of seeks that's needed in order to access all of our data.
So we know that the number of seeks possible to access the data is going to be determined by the maximum height of the tree. We know the height of the structure decreases by a factor based on the order of the tree. So the height of our structure is always going to be log base m of n, because at every single point we're decreasing by a factor of m. So if this is log base 100, every time we're decreasing by a factor of 100. Therefore, we know the number of seeks that's required is going to be log base m of n seeks.
And this number of seeks is going to be extremely low, because many B trees are going to run in order of 1,000 or more. So if we consider a B tree of order 1001, we're going to see that that tree is going to take a number and break it up by however many commas are in that number. So if you have 3 trillion pieces of data, you've got 5 different commas in that number, which means you're only going to have to do 5 seeks to look through all 3 trillion pieces of data. This is absolutely amazing, given how much data you can store and the small amount of disk seeks you need to do. In comparison, if you had that much data in an AVL tree, you'd have to do over 30 seeks. So a B tree is an optimized algorithm to optimize around the idea of doing as minimal disk seeks as possible when all of our data can't fit in main memory. It's a little bit of a hybrid between a classical tree and a pure disk algorithm. So we have the best of both worlds by combining 2 different algorithms we know. So we'll do a little bit more about B trees as we look at more algorithms that involve seeking on disks. But largely, we want to make sure that you have an idea of exactly one algorithm that works really well under conditions that we don't normally account for under big O notations. Next time, we'll talk more about how to develop other algorithms that build upon 2 different ideas. So I'll see you then. This week, we're going to talk about an entirely new algorithm that's going to combine some best properties of different algorithms. The best way to introduce this algorithm is to just think about a whole bunch of data, a whole bunch of numbers that we might want to insert into our algorithm. This magical algorithm, this magical data structure, is going to accept numbers or any other type of data that's comparable. Let's look at an example. So here we might have the number 3, the number -17, the number 42, pi, maybe e, maybe the number -10, maybe even the number negative pi. These are all numbers. We could think of any type of data as long as it's comparable. In this data structure, we don't want to maintain a total ordering. We don't want a sorted piece of data because we know that sorted data takes a really long time to maintain. Instead, the only operation we want to care about in this is we want a data structure that can remove the minimum value and do so quite efficiently. So if I do a remove operation on this data structure right here, I can simply say remove, and it's going to remove -17. And then if I do remove again, it's going to remove -10. If I remove again, it's going to remove negative pi. Notice that every single time the remove operation is not having any parameters, it's simply going to take the minimum value found in the entire data structure and remove it and return it back to the user. We want to optimize for this to build ourselves something called a priority queue, where every single value can have a priority, and we can remove based on the value that has the highest or lowest priority. To understand exactly why we want to build this, we can look at some of the classic data structures we already talked about. Here's 4 of them. We have right here an unsorted array and an unsorted list. And we can see that these lists have great insertion times, but terrible remove min times. Because we have to search through the entire element, the entire list, to actually get at what element's the smallest element. On the other hand, a sorted array and a sorted list has the ability to insert into that list in a very slow manner to maintain that sorted order, but then we can always remove the front element, the smallest element, in O of 1 time. So unfortunately, both of these have an O of n operation, which is an operation we'd love to avoid using. Instead, we're going to try and build a data structure that we can do both operations in less than O of n time. To do that, we're going to think about using something like a tree. A tree can be maintained just like our binary search tree that we've talked about earlier, in the sense that there's always a left child and always a right child. Though the ordering of this tree is not going to be the strictness of a binary search tree. Because remember, in a binary search tree, we have a detailed explanation of exactly what we need on each side, and we find that that structure is going to lead to some performance decreases that we're not going to find acceptable. Instead, we can go ahead and build out a new data structure by using the idea of a tree and sticking one property on it. Specifically, we're going to call this new type of tree a heap. And the heap's going to have a few properties. The first property is a binary tree T is a minimum heap if either the tree is empty, so either we have a tree that has no nodes, or we have a tree that has both a right and a left child, such that both the left and the right child nodes are larger than the root node. So all we care about in a heap is everything underneath our current node. All of our descendants must be larger than ourselves. We don't care anything about our siblings or anything that happens in another part of the tree. The only property about the heap that matters is everything that's a descendant from a node has to be larger in a min heap or smaller in a max heap than the node itself. So what that means is that if we look at this heap right here, that everything on the left-hand side is greater than 4. We don't care anything about the right-hand side when we're just looking at the left-hand side. Likewise, everything on the right-hand side is going to be greater than 4 as well, not caring about anything on the left-hand side. And this, of course, applies recursively. So everything on the left child of 5 is going to be greater than 5, not caring about anything else in the tree itself. All we care is this local property that the parent is going to be smaller than all of its descendants. This property we're going to actually represent using a clever data structure, because we would ideally love the performance of an unsorted array, some of those O of 1 great guarantees for lookup, that we don't have necessarily on, that we absolutely don't have on a binary search tree. So what we'll do is we'll always ensure a heap is a complete tree. Remember, a complete tree is going to be a perfect tree with every node filled in up until the last level. And in that last level, we're going to have all of the nodes pushed to the left. So notice this complete tree right here. Once we have a complete tree, we can go ahead and map that tree entirely to a data structure that we're very comfortable with. When we have this tree in memory, we're actually going to store it as an array. So specifically, let's look at this mapping. When we have this tree, we're actually going to represent this tree in memory as an array. So if we look at this example, we see that here 4 is going to be the root of the tree, and it's going to be the first element in the array. 5 and 6 will be the next 2 elements in the array. Then the 4 children of those elements are going to be the next 4 elements. And notice from the color degradation, we have 5 and 6 are both greater than 4. All of these nodes are going to be larger than their parent nodes. What I'm going to do is I'm going to actually not think like a computer scientist for a second. And I'm going to start indexing this structure from the value 1. And just so I don't even confuse myself, I'm going to go ahead and put a 0th index into this, and I'll just mark it with an X to denote I'm not going to use it. So here's index 0, 1, 2, 3, 4, 5, 6, 7. So given any random node, so let's look at this node 9. It has an index of 5. If we know the node's index, let's look at where its parent is. The parent of the element 9 is going to be the value 5. So the value 5 is here at index 2. How do we get from 5 to 2? Well, that looks like integer division. So 5 divided by 2 using integer division is 2. Let's look at the other child. 15 is the other child. 15 is index 4. 4 divided by 2 is also 2. So inside of our array, we can always navigate to our parent, not by having a parent pointer, but we know our parent is equal to our index divided by 2. Likewise, we can navigate to our children the exact same process by inverting this equation. We know our left child, given a parent, is going to be equal to I times 2. So looking at the value 20, for example, we know that 20 doesn't have a left child because 7 times 2 is going to jump to 14. Looking at the value 6, above 20, 6's left child is 7. So 6, 3 times 2 is 6. So left child can be gotten by multiplying our current index by 2. Our right child is going to be gotten by multiplying our current index by 2 and then adding 1. So what we have here is the entire memory representation of our heap is going to be entirely an array. all we're going to have in memory is our array. We're not going to have the tree structure in memory at all. But when we're actually doing the analysis, we'll draw it out as a tree because it's going to be way easier to think about things in a tree. Notice that we have the exact same tree structure we've had before. This is just like the binary trees you learned about earlier. But now we're going to shrink this binary tree into an array. We're going to have special properties on this array so that we can always go to our parent and child quickly. And we know that these operations all have simple mathematical formulas that allow us to compute them extremely quickly. Because everything's a power of 2, we'll see that computers actually do this even faster than we can imagine. So this is a setup for a heap. In the next video, I'm going to talk about how we can actually insert data in the heap and maintain this heap as we're building our priority queue data structure. So I'll see you then. Now that we understand exactly what it means to be a minimum heap, let's go ahead and think about how we might build one through a series of insert operations. We're going to use an existing tree and see how we insert into that tree, and then we'll generalize this out to understand how we can start with an empty array, insert to that array, and create the tree itself. So in this next example, I'm going to do 2 inserts, and you'll notice after every single insert, I'm going to go ahead and, as part of doing the insert, check to make sure that every level of my minimum heap is balanced and that the minimum heap property maintains true. We'll do that after each of the 2 inserts, and we'll see what elements need to be swapped. Let's look at this example. So I'm going to go ahead and insert the element 8 initially. So to insert 8, I'm going to go ahead and just put 8 down at the very last element inside my array. So putting this at the first empty element, or the last element inside of my full list of array, I know that this is the same as representing this element inside my visual model, inside the tree model, as putting an 8 right here. What I need to do now is ensure that every single parent has a smaller value than the node I just inserted. So here we look at 8 to 7. We see that that value is smaller, and we're good. We know that 7 is smaller than 6 and 6 is smaller than 4 because of the insert operations that happened previously. Now let's insert a second element. Let's insert the element 3. So inserting 3, again putting 3 at the end of the array, and then represent that in our tree model as the left child of 20. Here we have a problem. Now 20 and 3 are out of order. 3 is a smaller element of 20, which means it needs to be the parent node. So to fix this, we simply just swap those elements. So to do that, we find the parent node inside our array and swap 3 with 20. Now 3 belongs here, 20 belongs at the end. We can do that again moving up the tree. Looking at 3 versus 6, again this is out of order, so we go ahead and swap 3 and 6. We do this in the array, which would update our visual structure with 3 being here and 6 being here. Next thing is we swap 3 and 4. 3 now goes at the top, 4 goes here. In the visual structure, 3 is at the root, and 4 is on the right child of the root. At this point, we successfully inserted elements into the array. We maintained the heap property in the tree that we make from this array. And we see we do this through repeated checks on whether or not the parent node is smaller than the node that we just inserted. Let's look at the source code to see how this was done. The first thing we need to do every time we insert an element is check whether or not the array is large enough to accept this element. So here on line 5, you're going to see that we're going to check the size of the array versus the actual capacity of the array. If they're the same, we don't have room to insert, and therefore we need to grow the array. So the array is an unordered array in a data structure sense. So being an unordered array, that means that we need to think about how we need to expand it. Going back a couple of weeks, we know that to get the O of 1 amortized runtime performance, we absolutely have to double the array every single time. In doubling the array every single time, that means that we are going to have to ensure that we add a whole new level to our heap tree. So what this looks like is the slide that I have next. When we double the array, notice that our old array is going to contain all of the elements in the blue and orange layers. Here, when I filled up this last blue layer, I need to expand the array to add an entire another layer of the tree. This is equivalent to doubling the size of the array by making a left and right child at every single node. By adding those 16 elements in a tree that already has 15 elements, plus a node right here at the beginning to denote our 0th index, we have an array that grows from 16 to 32, then 32 to 64, and 64 to 128. We're doubling the size every time, so we know that this is an amortized O of 1 operation as we're running this insert algorithm. So we know how to grow the array. We know it's amortized O of 1. Let's look at the next chunk of the code. The next line you're going to see is line 8. We have the item is going to be, this is our array. We're going to insert at the end of our array the size of our array added by 1. We're going to insert the key at that location. Only then do we go ahead and heapify up. This is the name of the function that we're using to ensure that the heap property is maintained. Notice the input into heapify up. It is size. It is an index into the array. So we know it's an integer index. That's what we're going to heapify up on. It's not a value. It's actually an index. So we can call this parameter an int index. And this parameter is going to then be checked to make sure on line 3, our base case, that we're not at the root node. So remember, the root node is going to be the index 1 because we've skipped the index 0. So if index is greater than 1, we're not at a root node. And then if our value is smaller than a parent value, we go ahead and swap those values. And then we heapify up on the parent node to continue this recursive operation. So the parent of index, which remember, this is the floor of our index divided by 2, is going to be called to continue our heapify up process. At the end of our heapify up, we've either reached a root node and swapped the node we just inserted all the way up to the root, or we've swapped it to the correct location and we can stop running the algorithm. In both cases, we ensure that the heap property is maintained by the time we finish this algorithm. So now you know one of the 2 basic operations on the heap. You know exactly how to insert it. In the next video, we'll dive into how we can actually remove from our heap by removing the minimum element. So I'll see you there. At this point, you know what it means to be a minimum heap, and you know how to insert an element into the heap. Let's go ahead and remove an element from the heap. To do so, we are always going to be removing the minimum element. There's no operation on the heap that we can do except for removing that minimum most element. So to do so, we're going to go ahead to figure out an algorithm to take the top element of the tree, the root of the tree itself, and actually maintain the heap property even after removing the tree. So let's look at an example of removing a couple of nodes. So here's the tree we had in the previous video before we did any inserts. Now I want to remove minimum on our root node. So removing minimum is going to take 4 out of the tree. To do that, I'm going to go ahead and use a clever approach of actually just swapping the very last element in our tree with 4 to ensure that we don't mess up the tree structure itself. So as we remove min, I'm going to take 4 out, and I'm going to put that very last element, 11, into this tree. So doing that means that we have a complete tree still. We haven't ruined our tree structure. We've just ruined the order. In the previous example, we did a heapify up to do insert. Here, we're going to heapify down to do a remove minimum. So looking at our root node, we need to compare it with the child and take the smallest of the 2 children and swap the smallest child with the node above it. So here, 11 and 5 needs to get swapped so that 5 becomes the new root and 11 becomes the left child. Here we can then compare against the next level, 11 versus 9. 9 is smaller. We need to bring 9 up and bring 11 down. Here, 11 is smaller than both 14 and 12. Therefore, 11 has found its proper spot, and we've maintained the heap property. Let's do one more example here on this slide to understand exactly how this works. So going through a second example, we're going to remove min again. Removing min a second time means that we're going to remove the element 5. So 5 gets removed, and 12 becomes our new root node. We remove 12 entirely from the tree. What this means is here, we're going to be updating the array every single point of the way, but I'm here just updating the tree to make it simpler. Looking at 12, we're going to compare our 2 children nodes. Here, 6 is going to be the smallest element, so 6 becomes the root, 12 becomes the right child. Again, comparing the 2 children of 12, we have 7 versus 20. 7 is a smaller element. We swap 7 and 12, bringing 7 down here and 12 here. So again, we've maintained the heap property by doing a series of heapify down operations. It's going to ensure that after we finish doing our remove, that we ensure that the tree is a complete tree and that every single level has nodes whose the smallest element is the root node, and larger elements are always below that root node. The next thing we can look at is how do we actually run this? What's the actual code? Here, looking at the code, we see the code's really simple for remove min. The first key operation here is we're going to swap with our last element. The second key operation we're going to do is we're going to heapify down. So this is what restores the heap property. And like heapify up, we have a helper function that's going to do this. Heapify down, again, always starts with the root node. So we know exactly how to begin the call to heapify down. Looking at heapify down, we'll go ahead and start this at element 1, the root of the tree. We're going to heapify down, check if it's a leaf node. If it is not a leaf node, we know that we need to compare against the children. We're going to compare whether or not the item at our current index is going to be the item at the minimum child's index. So we want to check whether or not our current item is larger than the item of this current smaller. If it is, then we can go ahead and need to call our heapify down recursively after doing the swap operation on line 6. So the very last thing we're going to do is we're going to heapify down again on an index. So this will be the min child index, which says that we are going to heapify down by swapping the element with the minimum of our 2 children. In doing that swap, we're going to ensure that the heap property is maintained because the smallest element among the 2 children is now placed on top. So we know after this swap that among the subtree that includes our root node and our 2 children, that the root node is the smallest. Then we need to recursively continue down the path that we did the swap in. After doing this recursive operation, we know by the time we reach a leaf node that we found the proper spot to restore the heap property of this tree. So through 2 really clever algorithms, inserting using heapify up and removing minimum by using heapify down, we're able to maintain a minimum heap through a series of simple tree operations that allows us an extremely efficient structure to maintain an order inside an array without having a totally ordered array. This is going to be a really useful property, and we're going to start building properties on top of heaps in the next lecture. So I'll see you there. Now that we understand the basic operations of a heap, let's understand why we want to use a heap over other data structures, even though this looks remarkably similar to a binary tree. The main reason we want to use a heap is the idea that we can be really, really efficient about actually building a heap from the heap operations we have. So let's consider an example where we want to build a heap out of a string. So if we look at this example, I have the string build heap now. And this string is simply an unordered array, just like we've seen before. And this build heap now operation is just some characters that are not ordered whatsoever. And I have this build heap now also listed out in our tree format right here. So in all of this, we can think of the 3 different ways that we might be able to do an insert. The first way we might be able to do an insert into our heap is we could simply sort the array. So if we have a sorted array where the smallest element's at the top and the largest element's at the end of our array, then we have a heap. By definition, if the smallest element's at index 1, then it's going to be smaller than everything else later in the array. So this is good, but it runs an in log n time. We don't have time to do a search if we really want to make an efficient algorithm. The second operation we can think about is what if we just called insert a number of times? So if we call insert every single time, we're going to have to perform a whole bunch of heapify up operations. In fact, we're going to do in operations that each take log n time to do the tree operation. So this, again, multiple calls to insert is going to cause an n log n runtime. Again, an algorithm we just don't have time for. The last thing we can do is we can think of, can we do better with an O of n operation? So thinking about these things, we can think about a third approach that involves combining two different ideas to create a heap out of a string or out of any unsorted list that were brought in. So if we take a look at this example, we can see that the first thing is we can sort it. Second thing we can do is do a build heap by using heapify up. The third example is really, really clever. Let's think about only using the heapify down operation. So by only using the heapify down operation, what we're doing is we're saying that it doesn't actually matter what's in our very last level of the tree. Because the very last level of the tree means that everything here is already balanced and it has the minimum heap property. And in fact, it's not just the very last level, but it's the very last level and any nodes that don't have children. So this includes the node E here in the tree as well. So this is everything up to the parent of the very last node. So only the first half of the nodes in the array, so only things in the first half of the array needs to actually have their heap property restored. Because remember what heapify down does. Heapify down takes a node and makes sure that that node is placed down inside of our tree in the proper location. In doing so, the first node we have to look at is H. Because looking at the node H means that we need to ensure that H and the subtree that's rooted at H is a heap. In this case, it is indeed a heap already. Then we can simply look at D. At D, we say, is D smaller than both N and O? And only if D is both smaller than N and O is the heap property maintained. Here it is also maintained. We can go back to the previous slide and kind of keep looking at this. We can compare L with A and P. Here we can go ahead and swap A with L. Notice now we've maintained the heap property, doing this in the array as well. We swap A here, L goes down here. And at this point, we know that everything on the bottom two levels, everything here is a correct heap. So what we were able to do is we were able to just do three operations, three heapify down operations, to ensure at this point in time in the tree that we have a correct heap. Next, we only need to go and finish up the very last three elements. And in finishing up those last three elements, we're able to perform a series of just n over 2 heapify down operations. And we know that after heapifying down, that everything underneath our current node is actually already balanced. So because we're doing just n over 2 operations, we know that if we're doing n over 2 operations and the amount of work that we're doing per operation is capped so that we're not doing any more than about constant time work at each operation, we know that we can actually build a heap in O of n time. So the key reason that we actually care about building heaps and we care about the heap algorithm is the fact that given any sort of data structure, any array representation, we can build a heap notation of that in just O of n time, far shorter than sorting the array, far shorter than inserting into a binary tree. So that means as we're thinking about algorithms, if we need to know the minimum series of elements in a list, we can do so with just an O of n operation. So we'll dive into the analysis of this and how each of these operations perform and why we care about the heap in the next video. So I'll see you there. One of the last bits to talk about a heap is to really dive into things we can do with a heap. Because what we know right now is we know that we can do an insert and remove operation by just doing simple tree operations. From our knowledge about trees, we know that these are log-in operations because we have a complete tree. The other thing we know is we can actually build a heap in O of n time. So we can build it in linear time, which is a fantastic result, and it leads to us actually doing interesting things with a heap. One thing I want to dive into is one interesting algorithm you can use by using a heap, and this is the heap sort. So looking at the heap sort, we're going to look at how we can actually build a sorted array by exploiting the fact that we have a heap. Let's dive into this example. Doing a heap sort is going to be 3 steps. The first step is we want to build a heap. And to build a heap, we can do this operation in simply O of n time to create a heap out of a list of elements. The next thing we need to do to actually get at the heap, a sorted list in our heap sort, we need to call in calls of remove min. So once we've built the heap in O of n time, we can call remove in min for log n time each time. So what this means is we have a log n operation every n times for in log n runtime. And then only if it's needed, which may not be necessary, we may want to swap elements to order our list in the proper way, either ascending or descending. So notice that if we have a heap and we continually call remove min, we're going to get at a list that's going to have 4 as the minimum element, then 5, then 6, then 7, then 9, and so forth, by continually removing minimum from our tree. We know the slowest operation here is build heap, which takes n time, but the log n time is going to be required for every single remove min operation. So in the very worst case, our running time is going to be n times log n, because we have n operations of log n time, which is going to dominate the building heap call of n time. So even though we can build a heap in just O of n time, we can actually do what's called a heap sort in an optimal time for sorting in log n time. We care about this sort because it's often going to be very convenient to do this sort entirely in memory. If you're clever about using this 0th index that we leave completely empty, you can do a heap sort without using any additional space than the space you have in this array. This means as long as we have our data in any format that's in an array, a heap sort is going to be an ideal sort that allows us to order the data and provide some benefits for being in memory, and will give us some advantages if the data structure is already semi-sorted. So we've figured out how to actually understand what it is to be a minimum heap. We figured out how to insert into a minimum heap, how to remove min from a minimum heap. We understand the running times of minimum heap. And now we understand some application of a heap in a min sort. So what we're going to do next is we're going to start using all of these concepts to build something really great. So next week, we're going to dive into what it means to have one more algorithm, a disjoint set. And then we're going to finish off this semester by going in depth in graphs. And graphs is an amazing data structure that's going to unlock a lot of potential and allow us to solve a lot of really interesting problems. So I'll see you then.